Surupendo, I couldn't hear you.
Suru, this is Sandeep.
Hi,
Thomas
Sandeep.
want to ask some. Yeah, hello, Thomas, Professor Mandal. Let me.
Am I audible?
Yes, yes.
Yeah. Now we can hear you, Suru.
I think my earphones malfunctioned. Okay, sorry. Yeah. So welcome all to the day 5 of Fire 20. Yeah. Hi, Sandeep. Yeah. Actually, he couldn't hear me. Okay, so let me restart again. So welcome to the day 5 of Fire 2020. Yeah. Okay, so welcome to the day 5 of Fire 2020, and next we have the HASOC presentations. So that will be chaired by Professor Thomas Mandel, and so I hand over to Professor Mandel. All right.
Okay, I hope I'm audible well. So welcome to FIRE. Thank you, Surupendo, for the introduction and for the technical setup. Very nice, everything. Yeah, this last day of FIRE, and we are happy to have participants here. We worked many months to provide our benchmark for you. And now this is coming to the last step. We can hear many presentations, and we can learn, participants can learn from each other and see what have others done and what can be improved in the future. As you know, this organization of HASOC was a joint collaboration of many people. Many people participated. I see Sandeep here in the list who has worked a lot for that. So thank you, and thank you to all the others who have worked on that. I mentioned the names already in the overview presentations. And now, actually, I'm very curious to hear about the presentations of the participants. So I think we should start. There is some issues we have because of limitations of services and this and that. Some talks had to be reported, and we hope we can play them at the scheduled slots. And then we start without further waiting. And if it's possible for you to turn on the video, do it. If not, if you have bandwidth issues, just let it turned off. Then I would suggest that we start with the first talk by Surendra. Surendra, you have the micro on already. So yeah, maybe please start the screen.
Hi, Thomas. So, yeah.
Hello, welcome. Suru, let you open your screen, hopefully. Yes, we can see it. Yeah, visible. Great. Please go ahead. Thank you.
Thank you. Yeah. So, hi, good evening, all. This is Team Hate Detectors. I'm here to present our work done as part of the HASOC shared task. So, let's get started. Okay. Yeah. So we've titled our work as hate speech detection using traditional machine learning and transfer learning approaches. So the justification behind the title would be clear as we move forward. So first things first, we'll have a look at the problem statement. So basically the problem statement, we have two subtasks in this shared task. The first subtask is basically we are given a post from social media. We have to label it into one of the two labels half and not, denoting hate speech and non-hate speech respectively. So the next subtask is to basically within the half class, we have to now perform a finer level of classification into profane, hate speech, and offensive text classes respectively. So basically the first one would be a binary classification task, and the second one would be a multi-class classification task. So as part of this task, as part of the contest, we've tried approaching. Sorry.
Surendra, microphone is a little bit, there's a little background noise. Maybe try to hold it tighter or something.
Oh, sure.
We can hear you, but there's a lot of inference. Okay.
Is it okay now, sir?
Yeah, that's good.
Thank you. Yeah. So as part of this contest, we've tried approaching this problem in two directions. One, using the classical machine learning models for which we've chosen SVM. to using transfer learning. So transfer learning using BERT and other variants has revolutionized the entire NLP community now. So we tried to experiment with that as well. Then we also tried to highlight the importance of the monolingual model over a multilingual model. And also we tried to highlight where which model could be applied. Then we also highlight the importance of having a larger data set to this task. So here we've picked some examples from the data set basic for each of the labels. So we can see that there's a swear word common in all the examples. So the point I'm trying to make is that a simple swear word based rule based approach might not work as efficiently as we would need it to be. Also, my teammate and myself tried annotating some of the posts on our own, and there were actually quite a few disagreements among ourselves. So, and this was especially in subtask B. So the boundaries between these fine-grained classes is not well defined and is difficult to capture by the model. So moving on to the dataset description now. So as I mentioned previously, there are two subtasks, subtask A and B. Subtask A has two labels, half and not. So as part of this contest, we've tried using two datasets, one which was provided by the HASOC organizers themselves, and then another one was termed OLID, which was proposed by Offensival last year. It basically has 4,400 half posts and then 8,840 not posts. So that was for subtask A. And OLID was only available for English, so we've used it only for English. For Hindi, we only used the one provided by HASOC. And for subtask B, there are 4 labels: hate, offensive, profane, and none. And we haven't additional data set for this subtask. Now, this is the label-wise distribution of the data. Then we can clearly observe that apart for English subtask A, all the other data sets are highly imbalanced. So if so basically we should have a mechanism to tackle this, else the model will be biased towards the majority class. So now moving on to the methodology. Since the data is from social media where the posts are very informal, pre-processing is needed in an attempt to standardize it. So the pre-processing pipeline we followed is as follows. So first we do URL removal and then user mention removal. Then we move on, then we convert the emojis and the emoticons in the text to a meaningful version of them. I mean, meaningful words. Then we decompose the hashtags into its corresponding words. We lowercase out the entire text. Then we remove the unnecessary symbols. Then we remove stop words. And finally, we perform elongation mapping. So an example for elongation mapping we've mentioned here. There are 3 variants of the same word "yeah" in the data set, which actually have the same root word. Which actually have the same root word "yeah." So elongation mapping basically takes care of this. And for Hindi, we haven't performed elongation mapping. We've performed stemming instead. Yeah. So moving on. As I mentioned previously, we've tried 2 main approaches. One, the traditional ML models. We experimented with logistic regression, SVM, decision trees, and so on. But finally, we zeroed down onto SVM because that was performing well. Then coming to transfer learning based approaches, it was basically based on BERT. And for Hindi, we've used a transliteration tool and also tried experiment. So finally, we performed experimentation on both the original Devanagari version and also the transliterated version as well. So that was for subtask A. Now coming to the SVM based approaches. So everything done from this section would be on the pre-processed data. So there are 2 steps in the pipeline. One is the sentence encoding part and the other is the classification part. In the sentence encoding phase, we try to convert the post or basically the input text into a vector, which captures the semantic meaning of the text. So basically this vector would have all the information about the input sentence. Of course, this is an ideal situation and the quality of the vector actually depends on how good our embedding scheme is. So we've tried 3 embedding schemes. One is the universal sentence encoder. The other is the TF-IDF embeddings. The third is the average of all the word level fast text embeddings in the sentence. So for this, we basically tokenize the sentence into tokens. We get the token level fast text embedding, and then we average it out to get the final sentence encoding. Also, the universal sentence encoder has been only done for English. And also, one thing I wanted to mention, we only experimented on Hindi and English datasets only. We haven't performed our experimentation on the German dataset. Now moving on to the classification phase, we fit the vectorized data, which has been, which is the output of the sentence encoding phase, onto an SVM model. So some model specifics here for the hyperparameter C, we did grid search, and then to get the best model, we did the k-fold cross validation. Now we pointed out earlier that the data set was imbalanced. So to tackle that, we tried two modes of loss calculation. One is the class balanced loss. The idea here is that we want to make the contribution of all the classes to the loss function same. So basically the loss value same. So we scale up the loss values of the samples from underrepresented class, and we scale down the loss from the overrepresented class. The scaling is now based on a factor which is inversely proportional to the number of samples in the class. So for an example, if the ratio of the number of samples is 1:100, then the contribution value from the underrepresented class would be scaled up by a factor of 100. So and the loss is calculated as a weighted sum where the weights are based on this scaling factor. So this is about the class balanced mode. The other mode is just the normal mode where we do not have any weighted sum. We just do a normal sum of all the samples in that mini batch or the batch. We will actually show in the results if this has actually improved the F1 score or not, the actual macro F1 score or not. Now coming to the BERT-based approaches, again, the experimentation has been done only on the pre-processed data. There are two options in BERT. One is to go ahead with a monolingual model. A monolingual model is basically trained on only a single language. It understands only the language which it has been trained on, and it cannot be scaled to others. Whereas a multilingual model, on the other hand, can understand multiple languages in the sense that, for example, the multilingual BERT model has been trained on 104 different languages. It basically tries to map the sentences from different languages into a common space so that it can cater to all the languages. So this is just a high level understanding. We haven't gone into the depth of each model in the interest of time. And now, so for English, we've tried both the multilingual and the monolingual models on two different data set permutations. One is the only I mean, one is the English 2020 training set, which has been provided by HASOC this year. The other is the English data set appended with the OLID data set, which I mentioned in the data set section. And for Hindi, we just experimented with the multilingual model. So when to choose what, we would just touch that upon in the discussion section. Now coming to subtask B, the pre-processing pipeline is same as above, which we did for subtask A. The data set was imbalanced as we pointed out previously. Actually, we did not experiment on, experiment with the BERT-based approaches for subtask B due to lack of time. So the only thing the approach which we followed for this is the SVM based one. So we tried two different approaches. One is to treat it as a 4-class classification problem. That is, we include the none label as well. So basically it's independent of, we are treating independently as the first to the first subtask. Then the other approach is where we take the subtask A's best performing model. We filter out all the not labels and we directly give it the label none. And then for all the half labels from subtask A, we classify them into the finer classes of hate, which is offensive, profane, and hate speech. So this would now become a 3-class classification problem. Again, we experiment with both the loss modes for this as well. So that was the methodology on the whole. Now coming to the results, all the results in the tables which we would come across now are on the public test data, which was released by HASOC. The actual leaderboard positions were based on the private test dataset, which was actually not released. So for English subtask A, the best performing model was BERT Mono, basically the monolingual BERT model on the OLID plus 2020 dataset. The macro F1 score was 90, around 90. And basically the best performing model from the the machine learning approaches here mean that it's the traditional one, which is the SVM based one. So the best performing one there was TF-IDF vectorizing plus the class balanced SVM on the appended data set. We got a F1 of up to 88 there. So then moving on to the subtask B's results, again the best performing one was universal sentence embedding plus the balanced class SVM model, which was actually outperforming the others. Then for English, for Hindi subtask A, the multilingual BERT model performed best. Then for English Hindi subtask B, the TF-IDF vectors on the class balanced SVM perform best. So we would touch upon some of these things in the discussion section now. Basically, in all, so coming, I mean, from the order of performance of all these models was SVM was less than the multilingual BERT, was less than the monolingual BERT, wherever applicable, in the sense that monolingual was only experimented in the English case. So the margin, the difference was around 2% and 1.2% of macro F1 score respectively. So we can see that the difference between the mono and the multi-BERT models is not too high. It's 1.2%. But the training time for multilingual model was slightly higher than the monolingual model. So in the cases where we feel training time is okay, I mean a higher training time is okay, and also I mean a slight performance dip of up to 1.2 here in this case is fine. We can definitely go for the multilingual model, which basically has the advantage that it's common across all the languages. So we can have one common model across all the different languages. Whereas in the case of monolingual model, it's faster to train, and it actually gives more performance compared to multilingual model, although the margin is slightly lesser here. So it's basically a design choice. So now going on to the second point, the class-based loss calculation has actually improved results in all the cases. I mean, the cases where the data was imbalanced. So in Hindi subtask A, we saw an improvement of up to 15% F1 score, which is actually quite significant. Then for English subtask A, we did not see improvement because this was expected as the data set was already imbalanced. So that was pointed out in the data set description phase. And also in subtask B, we saw a significant rise again, which is 12%, I think, in the English one. So now moving on. So adding a new data set, I mean, adding the OLID data set to train on has actually improved the macro F1 score by 1% in BERT and 3% for the TF-IDF plus the SVM model. So basically the TF-IDF plus SVM was the best performing machine learning model, just to recap. So basically adding a data set here indeed helped improving the score. So, and also for subtask B, 4-class classification model was actually classifying most of the texts into either none label or profane label, which were actually the majority ones. But then the 3-class approach, which we took, actually improved the scores and also reduced the bias towards the underrepresented classes. Then finally, the transliteration which we tried out actually did not materialize. I mean, the results were not, did not improve as such. So this is some discussion on the results. Then this was our final leaderboard ranking. So we can see, we really felt that the competition was higher this year. It was closely fought. The leaderboard positions were this. So yeah, moving on. So as part of future work, I think we can definitely try to implement BERT for subtask B, which we did not do this time. Then we can also definitely go for LSTM and CNN based approaches with attention or without attention, and basically we can compare it with SVM and BERT models. Then then also we can definitely try out a GAN based approach, which might work for this model. I mean, that's just a hypothesis. We did not experiment as such. Yeah. So if in case, so we would like to take an basically we would like to thank the HASOC organizers for giving us an opportunity to actually present our work in the conference. And also in case of doubts, you can definitely reach out to us on one of those emails. We would be happy to clarify them. Yeah. Thank you.
Surendra, great. Thank you very much.
Thank you, sir.
A lot of experiments, good description, so very nice. Universal sentence encoding did not so bad. That's also a multilingual model, right?
Sir, sorry, sir.
USE, Universal Sentence.
Yes, sir.
It's multilingual too. Oh, it's so good and surprising to see.
So basically, the reason why we've mentioned that in the the traditional approaches was the BERT-based model would be fine-tuned, right? I mean, but the USC model was just, I mean, we just used the frozen model to just get the embedding out of it. So that's the reason why we just put it there. But yeah, what you said is definitely correct, sir.
Very interesting to also do the loss balance. Very nice work there. Thank you. Any questions from the other participants? Could just talk or put in the chat or raise your hand, I think. Not the case at the moment. Okay, so thank you very much. Very nice work. And we move on to Pankaj. Pankaj, I think already sent, is present. Yeah.
Hello, good evening, everyone.
Yeah,
this
audible.
is Pankaj Singh.
Go ahead.
Yeah, I'll be sharing my screen. So
yes,
is my screen visible?
Yes.
So I will be presenting our submission on this HASOC FAIR 2020, and our paper is titled Joint Multitask Learning for Multilingual Hate Speech and Offensive Content Detection. I am Pankaj Singh, and I will be presenting this work on behalf of both the authors. So this was the overall data set description of the HASOC FAIR 2020, which we were provided this year. So we had 3 languages, and this is the number of tweets, around 3,000 tweets for Hindi, 3,700 tweets for English, and around so these were the number of the tweets, and these were the number of class distribution. For example, there was class imbalance where we had lot of not hate speech and offensive detection tweets, because that is also the real world scenario where we get such a similar situation where we have lots of data which is not hate speech and the less amount of data which is hate speech. And this is further granularization of the hate speech data set, where the hate offensive and profane 3 categories were there, and mostly. So this was the description, and we had 2 tasks in hand. First was to classify the text into hate speech and not hate speech, and the second subtask was to discriminate between hate, profane, and offensive post. And this is the data, some data pre-processing we have done before using the data for our training deep learning model. We have removed @ mentions because they did not make sense when we are using hate speech, because a specific usernames does not have any impact on whether deciding whether the text is hate or not. We replaced the entire URL with a single keyword, capital URL. We replaced this hash character from the words and use just only words instead of hashtag. And we used multiple spaces, so the data set was a little bit noisy. There were some cases where there were a lot of spaces, so we removed those multiple spaces if present in any sentence. So basically this is the architecture of our proposed system. We directly jump onto using this multilingual BERT because we have already experimented this multilingual BERT with other hate speech systems where it was performing better than the classical machine learning and other algorithms. So we did not experiment with the classical algorithms. We use multilingual BERT directly. So multilingual BERT is trained on 104 languages. It is like variant of the BERT which has 12 layers, and this is the output hidden heads, and this is the total number of parameters 110 parameters. So it is a variant of normal BERT which was trained on English, so it is trained on multiple languages. So that's why it is capable of handling multiple language words and have embeddings for those multiple languages also. And so we pass our query query in this the context will be the input sentence through our multilingual bird. We obtain a 768 dimensional vector, and we pass that 768 dimensional vector via a softmax layer to do our final prediction. So basically our task was classification in both the cases. So this was the overall architecture. And in some cases we also had to use some fully connected layers before softmax, because that was improving the performance. And this is our ultimate system architecture, where so finally our proposal was to use a single model instead of six. So basically we had six tasks in hand, two for each languages, German, English and Hindi, two tasks for each language. Total we have six tasks. So instead of training six deep learning models, what we did was we trained only a single multilingual BERT model. So we combined the corpus of Hindi, English and German into a single corpus, and we trained our multilingual model on this multitask. First task was to get the hate speech or not hate speech, and second task was four level classification, where first was a normal text, second was the three specific categories of hate speech. So basically we combined all the languages and all the tasks and trained only a single model. So this was the overall architecture, and this is the training or fine-tuning strategy. In original BERT, they have suggested that we should fine-tune the entire BERT at once, but that did not perform very well, because I think our data set was very small, so the loss was not converging up to a global minimum or some minimum. So what we used is, for initial four epochs, we trained only softmax layer and freeze the all the BERT layers. Then for the next few epochs, we trained the 12th BERT layer, and as the training goes on, we keep on unfreezing the BERT layers. So at the end, all the BERT layers were unfreezed. So this unfreezing was done layer by layer. So this improved the overall training and convergence of our deep learning model. So this was the results on our data set. So these results are on the test data set. So basically the organizers have provided this test data set separately. So the system was performing pretty well for all the languages of for the task one. If we see this accuracy will be 0.72, but there was a class imbalance present in our all the cases except for Hindi in task A. So we can say that we can measure this by F1 score. So this was weighted F1 score. For Hindi it was 0.62, for English it was 0.85, and German it was 0.75. So because the class balance was good in English, so the performance was better, and all other languages also performed good, but there was the performance was less than English. And these were for the task B. We have a precision of 0.35 in Hindi. English it gave precision of 0.51 and 0.43. So this was the overall results on our test data set, and we have used only a single model to produce outputs for all the task and all the languages. So this was test data set, and organizers have also published the results on the leaderboard based upon the 15% hidden test data set. So we did not had access to this data set, but organizers have published the scores. So I will compare our score with the top one, top one and top three average system. So this was the overall accuracy. So F1 score values which we achieved during the competition. What I wanted to explain with this table is although our system is not in the top three, and our best ranking was on this German subtask B, where we were placed at the fourth ranking at the beginning of the competition when the first results were published. And uh, uh, we can see that the difference between the top one system and our system is not much, but these are the advantage of using our system. We have a single model which supports multiple languages. So instead of having six model for six tasks and for two tasks each languages, we have a only single deep learning model. It is a more scalable solution as the number of languages in online platform increases. So what we are seeing is the online platforms such as YouTube, Facebook are supporting multiple languages, and we can comment and tweet and do all the social media post on multiple languages. So it is not limited to some languages. So if you want to build a scalable solution which will be deployed and online, so it is not like quite feasible to have one system for one language. So that will easily blow up the system, because if we deploy these online heavy deep learning models online for one each language, that will not be feasible. So this having a single model reduces the memory requirement. It also reduces the training time, because what happens, instead of training 6 models, we are using on training only one model. The training time also reduces, the memory requirements in terms of deployment and GPU memory requirements also decreases. So these were the advantages of using this single model approach. And we, as we saw from this table, we did not lose on much performance, although this was not the best performing system, but the differences between were not quite there was not quite very much. For example, it is 0.52 in German subtask. Our system gave 0.50, so there was a difference of 0.02. So in the conclusion, I would like to say that we have established this efficacy of a joint system for all languages and tasks, and we have successfully trained system for all the 6 tasks given in the competition. And we aim to develop a single system, and we want to include more and more languages, and we want to see what is the impact of adding more and more languages. Is it performing similar, or the performance goes down? And we want to test the limits of number of languages a single deep learning model and number of tasks a single deep learning model can support. So this is the presentation from our side. If anyone have question, I would be happy to answer.
Thank you very much. Thank you very much. Again, nice work. From what we see is that the multilingual model still gives best performance for English. So maybe
yes,
the BERT multilingual, it's really
yes,
best trained for English probably, right?
Yes. Actually, sir, it is trained on 104 languages, but we split the data set. For example, the component of the corpus in English is still significantly more than the other languages. So still it is best performing than the other languages.
Mm. So it's a good step for the other languages, of course. Now it's not so far away from the English performance, but there is still some room for improvement. But nevertheless, I think you explained very well the advantages of the multilingual model. Very nice. Any further questions?
Yes.
Questions from the audience to Pankaj? Just open your microphone or raise hand or type in the chat. No question at the moment. Okay, so thank you very much. And the next talk, as I see it right, is then from Kalaivani. Is that right, Suru?
Good evening, sir. Shall I share my screen?
Yes. Kalaivani, welcome. Great. Started. Yes, now we can see now.
Okay, sir. Thank you. Good morning, all. I am Kalaivani from SSN College of Engineering. This presentation is all about my work on multilingual hate speech and offensive content detection in Indo-European languages using Albert. So, this is the outline of my presentation. The main objective of my work is to detect and classify the hate speech and offensive content in Indo-European languages like English, German, and Hindi from social media comments. So here we done task 1 and task 2 for all 3 languages, English, German, and Hindi respectively. So the goal of the task 1 is to recognize if the message is hate speech and offensive or not. The task 2, the aim of the task 2 is to categorize the content into hate and offensive and profanity. We have to categorize into 3: hate, offensive, and profanity. So what is hate speech? it effectively hated against a group or a class of person. It extremely shows the abusive behavior and to reveal their identity of an individual or a group. So the offensive language is nothing but, so it seriously offends someone or a group. The profanity, you have to use the curse words, swearing words, swear with bad words to someone or a group or an individual. So this all comes under it's so why, what is the important of detecting the hate speech and offensive content? The first is the increasing usage of social media. So there is an immense growth of social media communication, so billions of users were used social media forums through internet. So this chart will shows the number of people using social media platforms from this year 2004 to 2019, and also represents some of the number of peoples were using particular social media forum. Social media significantly affect current day society. So even though the kids and school going children were used social media forums, they facing many problem, but they don't know how to handle their situations. So this leads to mental ill like depression, fluctuations, like etc. More and more users have been experiencing online harassment. So this chart will shows the percentage of people who are cyber bullied in each social media forum. So 9 percentage of Twitter, 10 percentage of this, and 37 percentage of Facebook. So this more and more users were having experience on online harassment. So this chart will represent the key issues from cyberbullying like being abusing alcohol or drugs, had they had suicide thoughts, they have developed their depressions. So still we are facing the problem of offensive content in social media forums. So social media companies and many researchers are open to resolve their issues. So the challenges is to identify the hate speech and offensive language detection from social media forums. So in this shared task, we did in three languages. We participated task 1 and task 2. So I'm here just giving some example, which one is hate speech and offensive. And in task 2, we have to categorize if it is hate speech and offensive. We have to classify that is which one is offensive, which one is hate, which one is profanity. So this is the task we did in English, Hindi, and German languages. So these are the challenges we faced while doing the shared task. Difficult to transfer the code mixed languages, especially Hindi. The combination of Hindi and English text. Some text, the Hindi language is also written in a Roman script also. So there is a imbalanced data, imbalanced data and ungrammatical sentences, the usage of slangs, URLs. So the native language written in the English in Roman format, especially in Hindi. Some words is separated as letters, misspelling words, prolonged words, and continuous letters, all that. So this is the input. The organizer provided the HASOC data set for Hindi, English, and German. So this is the trained data we used, test data. So totally we used for English 4,522, 2,009, 899 for German, and 3,626 for Hindi. So this is the category wise data set for Hindi, English, and German. Expect English, German, and Hindi, the data set were imbalanced. So in not category is 1,700 to 116. So we have to handle this imbalanced data. So these are the pre-processing and methods used. We did minimal pre-processing here. First, we removal the @ symbol, hashtags, punctuations, URLs, numerals, emojis. We convert all the text into uppercase into lowercase. We translate the German and Hindi languages into English language by using Google Translator. So here we used the method Albert. So Albert is nothing but it's a lightweight board for self-supervised learning language representation with K-train library. So use of this K-train library, you have to use easily to build the system for English, German, and Hindi language. So this is the lightweight wrapper in TensorFlow. It helps to build, train, deploy the neural networks, machine learning models, and deep learning models. It easy and more accessible. So in this task, we used Albert Base V2 model, especially. So this is the methodology. We follow these steps. First one, we have to create a transformer instant. For that, create a transformer object by using K-train. Um, and we set the model name. We used, I'm already said, we used the model Albert base V2, and we set the sequence length is 512, and we have to mention the classes argument with the list of target names. So the next one is the processing the data. So we have to process the data which is suitable for Albert model. For the validation process, we will separate the training data in for 0.2% from the training data and set the random state is 100. Next one, create a model and wrapper in the learner. We define a classifier with predefined weights and randomly initialized final layers that can be fine-tuned. The model will be wrapped in a K-train learner object. Use of this K-train learner object that will allow us to train, easily train and inspect the model and use it to make prediction for on a new data. So here we set the batch size is 6. The next we train the model. For that we used K-train fit one cycle method. So it will employs the one cycle policy, and we set the learning rate 3 minus 5, and we set the opposed to 5. The next we have to inspect the model. Based on that, we used view top losses. So here I mentioned one example ID 176. So in that statement, it will shows it will predict none, but the statement will be the offensive. So this by use of this method, we have to inspect the model. Next one, make prediction on your new data. For that we initiate a predictor object. So predict method will returns the predict class label, and predict probability will returns the predictor probability for each class. So this is the validation result for our model. We did task 1 and task 2 for all 3 languages, Hindi, German, and Hindi. This one is we translated the German language into English language and used the Albert model to predict the for classification model. This one is translate the Hindi language into English language. So in that, the accuracy is 0.91 for English task 1, 0.81 for task 2. German task 1 0.81. It's the same as the translated German language, also 0.81. So German 2 will better performed. The next one is the test sample result. Here the micro F1 score is 0.8 for English task 1, 0.5 for English task 2. For German language task 1, 0.76, for Hindi language 0.41. This translated German language 0.5, 0.4 for Hindi, 0.3 for translated Hindi task 2. So this one is the final private leaderboard result. They take 15% of data to evaluate. In that we scored 0.5 for English task 1, 0.2 for English task 2, 0.5 for German, 0.2 for German task 2, 0.3 for Hindi task 1, 0.2 for Hindi task 2. So I'm concluded that our team submitted. We got the score. Our team achieved the second rank for the final leaderboard test data, particularly in German language in task 2. In future, we will improve the performance by using different classification algorithm. We have to extend the systems to other native languages also. Thank you.
Thank you, Kalaivani. Very interesting. The translation approach was amazingly successful. So that is interesting to hear. you gave the batch size of 6, meaning 6 tweets at that time.
Yes, sir.
And epoch size 5 is really enough. That sounds very, very little, but
It's good,
loss
sir.
is good.
It's
Good.
good.
Is only the last layer retrained, or the previous layers are also changing their weights?
Previous layer also we did.
In the retraining, okay.
Yes, sir.
Oh, interesting, and nice examples we see. But really nice to see that the translation works so well. So that could be really a good way for future research. Yeah, any questions from the audience, from the other participants? Use the opportunity to learn.
Okay, sir.
Not
Okay,
the case.
thank you.
Thank you very much, Karavani.
Thank you, sir.
Our best regards to Tamil Nadu, and we move on to the next talk. I think we have now Jingxia Chao, and from China. There might be issue with logging in. Surupendru, is the recording or what is? Okay.
Yeah, he has sent a video. So let me just share it.
Excellent.
Just give me a moment.
Sure. So there is 2 more presentations now, and then we have our short break. And the first one is recorded due to access limitations. And people might sometimes also feel more comfortable with recordings. Suru sharing the screen. Okay, let's listen to the presentation.
I'm Yinjia Zhao. First of all, I would like to thank the organizers for giving me this opportunity to share my work with you here. My presentation is divided into 4 parts: introduction, methodology, experiment and results, and finally the summary. The possible reason for the holding of this merge, I guess, is because online social media platforms provide convenience for people to communicate, but the harm caused by the online hate speech and offensive language accompanying them is also significant. In this competition, we take part in Subtask A and Subtask B for English language. We use a model based on a bird. A live bird for self-supervised learning of language representations. This model combines the bird model with a specific network structure to further process the eigenvectors of bird output. During the training, we use the training data provided by Haskell 2020 as the training day third to train the model of this task. Finally, we use the stratified k-fold method to ensemble. Our model structure is shown in figure. First, we input the preprocessed text into the model through the input layer, and then vector representation is carried out. Vector representation is divided into three parts: word vector representation, text vector representation, and position vector representation. The Leaderboard model takes the addition of word vector, text vector, and position vector as input, which is further processed by the transformer encoding module. We then input the output of the last hidden layer of Leaderboard into BILSTM, and concatenate the output of BILSTM with the output of the last hidden layer of Leaderboard, and then through the ReLoop function map the split vector to the lower dimension in a non-linear way. After that, max pooling will be used to take the maximum value of each position in the vector on a timing sequence to obtain the feature vector. Finally, the feature vector will concatenate with the original Leaderboard output and input into the classifier. And in this experiment, we use the stratified k-fold ensemble method to train different data during training process, and extract different features during the process of extracting features from the model, as we can see on the slide, so as to enhance the generalization ability of the model and achieve the purpose of enhancing the performance of the model. The idea of stratified k-fold is k-fold cross-segmentation. Each type of data in the initial training set is divided into k subsamples. A single subsample is retained as the data of the verification model, and the other k subtract one sample are used for training. That is, to ensure the hierarchy sampling and the proportion of kinds of samples in the training set and the test set is the same as that in the original data. And the experiment and results. First, in order to eliminate the interface of irrelevant information in the tweet, so that the model can better extract text features and train the model more efficiently, we pre-processed the original training data provided by the official with an LTK tool. The main processing steps include remove number, stemming, remove links to address and special characters, and convert all characters to lowercase. And as for experiment starting, the pre-training model we use in the experiment is Leaderboard-based phase 2 from the Leaderboard serial model. In the process of fine-tuning, the main parameters are maximum sequence length and learning rate, the gradient accumulation steps, and batch size, as we can see on the slide. As for the results, according to official results, our team's Michael F1 score is 0.4994, ranked 13th place in Subtask A for English language, as shown in Table 1, and in Subtask B for English language, our team's Michael F1 score is 0.2412, Rent takes place as shown in Table 2. The end is the summary. For this competition, our team used a broad pre-training model to extract the semantic information features of text and further process the output features by using customized network structure. Finally, the stratified keyfold ensemble is used to improve the generalization ability of the model and the few model parameters, making the model lighter and easier to train. Our model achieves satisfying performance. In further research work, we will try to fine-tune about more hidden layers to make the model more suitable for specific training tasks, thus further improving the model performance. And in the end, we would like to thank the organizers for organizing this short task. That's all. Thank you, and thanks for watching.
Okay, we thank our participant Jingjia for sending. And we have one more presentation now, Suru, or is it already?
Let me see. Oh yeah, there's one more.
One more file, no?
Yeah.
Any discussions? Any questions for Jingjia? You can collect and send.
Let me just share my screen.
Oh, okay, again. Yeah. So we're happy to check the next presentation of Zijiao Chu. Thank you. Thanks.
Is this visible?
Yes, it's fine.
Okay. Just let me know if you don't.
Good evening. My name is Xiaozhi O. I'm from Yunnan University in China. It's my great honor to be here as a member of the contestants of the Haskell 2020 competition to make a presentation for my team's work. The title of our paper is Multilingual Head Speech and Offensive Content Identification based on Xlm Robot. Next, my presentation is divided into the following 4 parts. Firstly, we introduce the task in which our team participated. Based on the success of Haskell 2019, this year, the organizers once again provided 2 subtasks for English, German, and Hindi. Altogether, more than 10,000 alternative tweets from Twitter. We participate in subtask A for 3 languages. This task focuses on hate speech and offensive language identification, found for English, German, and Hindi. Subtask A is a coarse-grained binary classification, in which participating systems are required to classify tweets into 2 classes, namely NOT and HOF. The second part, we will introduce the overall framework of the model. Before talking about the model, we first make a brief description of the data pre-processed part. In our experiment, we use stratified sampling technology to randomly split or combine the training dataset. As shown in figure, we use a stratified keyword cross-validation instead of ordinary keyword cross-validation to evaluate a classifier. The reason is that stratified keyword can utilize stratified sampling to divide, which can ensure that the proportion of each category in the generated training set and validation set is consistent with the original training set, so that the generated data distribution disorder will not occur. In the experiment, we use five-fold stratified sampling. For our model part, we use the pre-trained multilingual language model, Xlm Robot. We first get polar output. We use PO for it in the model field. We discovered the limitations of both polar output and about time-rich semantic information. By extracting the hidden state of Xlm Robot, the last four hidden layers, and input into ordered neurons LSTM called OnSTM. Finally, we concatenate the polar output and output of OnSTM and submitted to a linear decision function for the final classification. The third part is about the experiments and the results of our team's participation in the task. The part where presentation the results and analysis of 3 languages that we participated in subtask A on the test set, and the official 15% private test set. The subtask A for the 3 languages is evaluated by following the Markov average F1 score of signal. The test set results of subtask A in 3 languages are shown in Table 1. For each language subtask A, we have performed 3 runs. Among them, run 1 means that we take the polar output of Xlm Robot as the final output. Run 2 means that we extract the last 4 hidden layers of Xlm Robot and input them into the convolution neural network and K-max pooling. Run 3 means that we extract the last 4 hidden layers of Xlm Robot and input them into OnSTM, which is also the system we finally submitted. Table 2 reports the leaderboard results of the best row of the subtask A in the 3 languages we participated in on the official private test set. This final leaderboard is calculated with approximately 50% of the private test data. We can also see the best score of the official leaderboard and our ranking. We can see that the results on the official leaderboard show that our model is very effective. In English subtask A, our model achieves Markov average F1 score of 0.5006 and only 0.0146 below the best score. In German subtask A, our model achieves Markov average F1 score of 0.5177 and only 0.0058 below the best score. In Candy subtask A, our model achieves Markov average F1 score of 0.52 and only 0.0137 beyond the best score. It can be seen from this response or model's generalization ability is very strong because it has shown excellent performance in different languages. Finally, we summarize this work in the experiment. We find the limitation of only using polar output as the Xlm Robot output to obtain deeper and more abundant semantic features. We extract the hidden layer state of Xlm Robot. The results show that our method is careful to improve the performance. Hello everyone, good ending of my. In addition, adding data from different languages can improve results. In addition to the above, there is a lot more for us to do. We will continue to improve our methods. This is the ending of my presentation. Thank you for your support and your kind attention. Thank you very much.
Okay. So I think we will listen to one more talk from the Team Hub or Huang. And after that, we take the break. So let's look at the time. And thanks for Suru. 8 minutes, we have another talk.
Very honored to be able to share the work of the Hubert team with you at this meeting. I will represent my team to show you our related work in the HASOC 2020 tasks. Our title is Hubert at HASOC 2020, Fine-tuning Pre-trained Transformer Language Models for Hate Speech and Offensive Content Identification in Indo-European Languages. Introduction. Since 2011 was known as the first year of the mobile internet, the number of online social media users has shown a spurt of growth. In the context of the ever-expanding user community coupled with the free and interactive characteristics of online social media communication, the negative effects of hate speech, offensive, and profanity in social media bring serious consequences. The focus of this short task research is to identify hateful or offensive content in English, German, and hidden comments posted on Twitter. The task goal proposed by the task organizer team is to identify hate speech and offensive content from the comment data side obtained from the online social media Twitter. An evaluation task for this task is the use of macro F1 score. We only participated in English task and German task. We used two fine-tuned pre-trained transformer models, Albert and Bert, for the English task and the German task. Since the task of the pre-training site comes from Twitter, the content contains many non-letter symbols. For example, URL, emotion, some non-letter combinations, numbers, etc. Subtask A. Subtask A is a course-created binary classification in which participating systems are required to classify traders in two classes. NOT, non-hate offensive. This post does not contain any hate speech, profane, offensive content. HOF, hate and offensive. This post contains hate, offensive, and profane content. Subtask B. Subtask B is a form-graded classification. Hate speech and offensive posts from the subtask A are further classified into three categories: O, F, N. Offensive posters under this class contains offensive content. P, R, F, N, profane. These posters contain profane words. HATE. Hate speech posts under this class contain hate speech content. Use macro F1 score for test result evaluation in tasks. We got the architectures of the Albert-based and Bird-based are both composed of 12-layer transformer. The models we used in the results we submitted were fine-tuned BERT and Albert. For Albert, the output matrices shape of the last 4 layers is the same byte size, sequence, hidden size. We got the 0-dimensional and 2-dimensional of the last 4 layers of the matrices. Then place them with the polar output matrices to obtain a new matrices. Finally, input these new matrices to classify. For BERT, we get the output matrices of the last 4 hidden layers. Then we receive the output of the last 4 hidden layers of BERT to obtain 4-dimensional output matrices. Batch size, sequence, hidden size received to the shape of byte size 1, sequence, hidden size. Next, input these 4 matrices into test CN network. After that, connect the polar out CLS with the 4 output matrices of test CNN. Finally, import the matrices obtained in the previous step into the classifier and a layer of subtasks. Submission results. Shown here is the final submitted result of our team and the top 1 result of the corresponding task. These results come from the results list published by the task organizer team. For the English tasks, we use our fine-tuning scheme for the Albert-based pre-trained language model and use it to complete the English subtask A. We apply our fine-tuning scheme on the bird-based and use it to complete English subtask B. For the German tasks, the pre-trained language model we used in the German version of the bird-based pre-trained language model. We apply our fine-tuning scheme to this pre-trained language model and use it to complete the German subtask A and subtask B. Conclusions. In our work, we have conducted experiments and researches on all tasks belonging to the 2 languages of English and German. We use fine-tuning Albert and fine-tuning bird-based task scene to complete this task. In the 2 subtasks A, the emotion orientation of the test is very different, and the scores of the results submitted by the contestants are generally higher than those of the test B. For the two subtests B, the training data is not only unbalanced, but also the emotional tendency of the test is similar, so the scores obtained by the model are generally low. In future work, we hope that better models and methods can be used to improve the effect of the identifying hate speech. Thanks.
Okay, so thanks to all. Recordings, nice, so interesting to combine the last layers into a CNN, nice idea. And now we have a 10-minute break. And after that, we continue with the talks. Any other issues, Suru, or that is all? Oh, fine, now, okay, so meet you here again in 10 minutes.
Yes, sir.
Okay, dear all. We can move back. I see that we have participants here, but there's also several visitors on YouTube, and there's also some discussion there already. So also greetings to the audience in YouTube and of course here in the Zoom room. And then we can move on. And from what I see now, we had some cancellations with the problem. I think we move now to the presentation of Zhao Chi O, which is also recorded. So again, I would ask Surupendo to play it.
Yeah, and I'm sharing my screen again.
And then we come back to the next live presentation. So please go ahead.
Speech identification. In our participation in the HASOC 2020, we aim to identify the hate speech in tweets. First, we fine-tune the XML Robot, a pre-trained model for sentence embedding, and extract the layer with the best performance for slicing and splicing, in order to make full use of both English and German corpus. We propose a multi-task method to optimize two classification tasks at the same time. There is the contents. Over the past decades, as global hatred and bigotry spreads through social media, insensitive minorities around the world are facing new and growing threats. Measures should be taken to reduce the separated spread of the hate speech on social. And the HASOC 2020 provides a film and a competition for multilingual research on identification of hate speech to solve this problem. And related works. There have several works for text classification, such as the logistic regression, supported vector meshing, random forest, and there are also pre-training models like BERT and Robot. Some of the early works use features like bag of words and characters, n-gram with relatively machine learning classifiers for detection, like Danker and Wissing and Hovey. Kim use CNN for sentiment classification. It requires very few hyperparameters adjustment and static vector to achieve good results on multiple baseline. McAvenny proposed a multi-view SVM approach that achieves near state-of-the-art performance, while being simple and producing more easily interpretable decisions than neural methods. An Xlm Robot comes at a time when there is a proliferation on non-English methods. Multilingual methods are a form of feature proofing that ensures the existing NLP infrastructure is able to scale to however many regions they choose to do business in. And what's new in Xlm Robot? The Facebook AI team released the Xlm Robot in November 2019 as an update to the original XML 100 model. Both the transformer-based language models both rely on masked language model objective, and both are capable for processing text from 100 separate languages. The biggest update that Xlm Robot offers over the original is a significantly increased amount of training data. The cleaned common crew data that is trained on takes up whopping 2.5 TB of shortage. We concentrate on detecting multilingual hate speech, which are written in English and German, and details our solution. We fine-tuned the Xlm Robot pre-training model for sentence embedding, and extract the layer with the best performance for slicing and splicing. To make full use of both English and German corpus, we further proposed a multitask method to optimize two classification tasks at the same time. The dataset of HASOC text A contains over 10,000 announced tweets, respectively, composed of user ID, tweets, and labels from Twitter through our analysis on the dataset. English datasets have a uniform distribution, while German dataset is uneven. We took part in the English and German subtask A, which involves building a core-scanned binary categorization model to test whether a text is offensive or insulting. Hof. If a text contains any form of unacceptable verbal aggression and profanity, it will be considered as Hof. Because there was noise in tweets in official datasets, which would affect the performances of model training, we cleaned the data before training. The steps are as follows. We keep the label, handle username and add beginning uniform as username, separate conjunction, turn emoji expression into the corresponding phrase, remove words that have no emotion meaning, remove all URLs, convert text to lowercase. Numbers are normalized to string as number. After data processing, we combine the English and German datasets as one dataset in order to improve the generalization ability of model. Let the model learn the real data characteristic distribution. The method of stratified sampling is adopted to ensure the training set and the valid set have the same data distribution. Besides, we divide 20% as a valid set, 18% as a train set. Table 1 shows the distribution of the Hof and Not. And we extract the feature vectors from Xlm Robot. After getting the embedding vectors of the text, we fine-tuned Xlm Robot to make it more suitable for the downstream task of hate speech identification. Xlm Robot has a total of 12 layers, which learn different semantic information. Generally speaking, the shallower the layers, the more word-level semantic information is learned. The deeper layers, the more generalized semantic information is learned. And the TC contains the semantic information for classification of the entire sentence. We try to combine TC with vectors at the certain layers to improve training performance. And at last, we choose the 12th layers to extract and combine and we take the 12 layers and slice and concact to TC, and at last it's through a softmax classifier. And we compare our model with 3 baselines. LR is a machine learning method to solve the problems of characterizing. We use it as a baseline classifier. And the hyperparameter C equals 1.2, and we use TF-IDF features of rate n-grams 1 to 6 for training the classifier. Svm is a binary classification model. The basic method is to solve the separated hyperplane that can correctively divide the training dataset and has a maximum geometric spacing. We use it as a baseline classifier for both English and German datasets. The configuration is as follows. We use a nano kernel, L2 regularization with a hyperparameter C equals 1, and the same TF-IDF features of word n-grams 1 to 6 to train the classifier. By LSTM models is implemented with 100 units. Adopt a sigmod activation. For training, binary cross-interpol loss function and Adam optimizer are used. As you can see, our Xlm Robot fine-tuned performs best in the English and the German datasets. Our system ranks 6th in German subtasks and 13th in English subtasks. Conclusions. We have proposed a new solutions with fine-tuned Xlm Robot for hate speech identification. Particularly, the output and hidden layers are slicing and splicing, which solves the sparsity of data and increases the generalization ability of the model in a multitask way. Experiments have proved the competitiveness of our method. And there is a reference of our paper. Thank you.
Surus, thank you very much for playing the video. And then I think we can move on without discussion to the next talk. That will be by Raja Lakshmi. See here? Not yet logged in, I think. So we move on. Shivangi will be the next speaker. Okay, thank you. So Shivangi will be the next speaker. Then, please, I see you logged in. Then let's move on and let us see your approach.
Okay, sir. Shall I present my screen?
Yes.
Sir, is the screen visible?
Now it's there. Go ahead, please.
Okay. Okay, so Good evening to everyone present here. My name is Shibangi Srivastav and I'm from Netaji Subhas Institute of Technology, Patna. And I'm here to deliver a presentation on behalf of my team. And the title of my paper is Deep Learning Model for Hate Speech Identification in Indo-European Languages. The co-authors of my paper are Mr. Sunil Soumya, my very prominent mentor, the assistant professor at IIIT Dharwad, and my colleague, Mr. Roshan Raj. So here is a short preview of my paper. I would begin with the objective of the paper. So we all know that the low cost, easy accessibility and high effectiveness of social media have changed the way we live. But the darker side of this comes with the rapid increase in cyberbullying rates and with people spreading hatred and threatening contents. Cyberbullying statistics of 2020 have shown that 42% of online harassment happens on Instagram, which has over a billion active users. Facebook and Snapchat also follow closely with 39% and 31% respectively. Also, the victims report anxiety, depression, and self harming after effects. So, it becomes extremely necessary to regulate and monitor such offensive content on social media. Okay, so we participated in both subtasks of all the three languages, which were English, Hindi, and German. So, moving on to the task description. The data set which was provided was collected from Twitter, and there were three languages, and each language consisted of two subtasks. Also, it was thoroughly covered by our organizer, so I would simply move forward. Okay, so here comes the data statistics. So the given graph shows the class distribution for subtask A for training data and testing data. So we can see very clearly from the graph that for the English language it was balanced, but for German and Hindi it was quite unbalanced. The same thing goes for the testing data as well. For English it was balanced, for German and Hindi it was quite not balanced. And if we look at the statistics for subtask B, we find that there were four classes: hate, offensive, profane, and none. And irrespective of the language, we can see that the dataset was heavily unbalanced, be it for the training data or for the testing data. So now we come to the pre-processing steps. So we started with the cleaning and filtering of the text. For that, we converted the text to lowercase first. Then we removed the redundant text, such as the punctuation symbols. Then we removed the RT symbol, which was the retweet symbol for the Twitter data. We also removed the URLs. We removed the alphanumeric characters and the apostrophes. After that, we went on removing the stop words. We applied stemming. We performed the tokenization, and we also created vocabulary. And this was followed by encoding and prepadding. So let's look at the approach that we have adopted for different languages. First, for the English language, in case of subtask A, we pre-processed the text. Then we used glove embedding. Then the output of this embedding layer was fed into the input layer of convolutional neural network. So we made this network using two convolutional layers, using two max pooling layers which were used to extract the features, and using two dropout layers which was used to prevent overfitting. And this was followed by flattening all the features by a flattened layer and then feeding it into a dense layer. After that, we simply performed the model training and then we got the prediction. So in case of subtask B, we adopted the similar approach, and one additional thing that we did was adding the Edison oversampling technique, because that was necessary to handle the heavily unbalanced data set in case of subtask B. So moving on, if we look at the results for English subtasks, so here we see that we performed and experimented with a lot of different models. Basically, there were three different models: CNN, bi-LSTM, and hybrid. Hybrid model was a combination of CNN and bi-LSTM. And also we tried different variations like using SMOT and Edison oversampling techniques, and we also tried on the unbalanced raw data set. So for the subtask A, the highest F1 score that we achieved was 0.84. And on the model that we have just discussed, And for subtask B, we achieved 0.54 FN score. Okay, moving on to the approach for German language. So for the German language, for subtask A, again we did the same thing. We pre-processed the text data. We used a fast text embedding, and this time we used a CNN layer, means the convolutional neural network. Then we simply did the model training and prediction. Then for subtask B, we again did the pre-processing, and all the things were same. Embedding was kept same, fast text, and we applied Addison oversampling technique. So if we look at the results, we again experimented with all the different kinds of models that we previously saw. So the highest, okay, it's hidden, it got hidden. Yeah, so the highest ever micro average score that we got in the subtask A was 0.75, and for the subtask B, it was 0.45. Discussing the approach for Hindi language. So for subtask A, we applied fast text embedding after the pre-processing, and for this case, we used bi-LSTM network. So to build this network, we simply used a bidirectional layer, and we used a dropout layer followed by a dense layer. Then we performed the training and prediction as we did earlier. And then for the subtask B, the embedding was kept similar, and the network we used was CNN, and with the additional Addison oversampling technique. So now if we look at the results, we saw that the highest FN macro was 0.67 for subtask A, and it was 0.36 for subtask B. Okay, so moving on with the hyperparameters that we used in our model. We ran our model for 200 epochs. We kept the wedge size as 32. The activation function that we kept was ReLU, and sigmoid function was used at the output layer. Optimizer we kept as Adam, and dropout rate was set to 0.2. Pre-padding length, we kept it as 100. Also, we kept the patience value as 2 for the reduced learning rate, and it was kept as 8 for early stopper. Now moving to the results and observations. So the given table shows the F1 macro average scores and the ranks of all our best 6 models that we obtained in all the 3 languages. So this F1 macro average score that is presented here in the table is calculated by the organization with approximately 15% of their private test data. So as seen in the table, our Hindi model outperformed all the other models, and we secured first rank in Hindi subtask A, and we secured second position in Hindi subtask B. The rest of the ranks are as shown in the table for different languages. Okay, so one major observation that could be made was that subtask B achieved a lower F1 macro average score every time, irrespective of the language, than subtask A. So the reasons for this could be the heavily unbalanced data set. Firstly, this is quite obvious. Second one could be the miniature differences in the 3 classes, which might have led to the prediction of lot more false positive classes. And also, the Hindi dataset was a code mix data, which was mixed with a lot of English words. But the embedding that we used was only for the Hindi language. So this could probably be a reason for the poor performance in subtask B. So finally, winding up with the conclusion, we propose different CNN and bi-LSTM architecture developed using word vectors of the relevant pre-trained corpus. The future scope for our implementation could be to improve the dataset balancing, because even after applying SMOT and Addison oversampling techniques, we couldn't quite improve the F1 macro average score. Further improvisation could be to tackle the identification of hate speech in multilingual tweets and posts on social media. We have open sourced our implementation of the best models at the given GitHub link. Lastly, this is the summary from our paper. And lastly, I would like to thanks and give credit to all the organizers who conducted this event very successfully. And it's really, I really feel grateful that I got this opportunity to participate into it. So thank you so much, everyone. Any questions?
So again, thank you very much, Shivangi, and very
Thank
interesting
you.
results again.
Thank you, sir.
We see that, yeah, of course, as naturally, there's some English words and also English Latin script in the Hindi data, right? And
Right,
nevertheless,
sir, right.
You did well with kind of a monolingual approach, and even were best at Hindi. But we've seen other previous participants
Yes,
who
sir.
had
Surprisingly.
we have seen other who had done the multilingual approaches like translation and USC or multilingual, but and
Yes, sir. That could be considered as a future work for our implementation. Definitely, sir.
On the other hand, maybe
Using
just dropping English maybe also was helpful. It could have been the case too.
Yes, sir.
We don't know, no?
Yes,
But
sir, of
interesting. That would be so seems to be very interesting for the future work to analyze what has happened here, because you just ignored it and got excellent results. So your model captures this stuff very well. And we see that there's a lot of work necessary for the imbalance, but the imbalance is just part of the natural data set,
Yes,
right?
sir. Yes, sir. Right.
Great. Any other questions for Shivangi?
Right, sir.
Let's see, any raised hands here, any microphones on? Not the case, I see. So I thank you very much. Also, it was very nice that you outsourced your code or make it openly available. I think that should be best practice for all participants. And then
Thank you, sir. Thank you so much.
Best regards to Bihar, and we move on to the next speaker, and I think it will be Sunil.
Okay, sir. Okay, sir. I will stop presenting now.
That's fine. Yeah, thank you. Is it right?
Yeah. Good evening,
Sunil.
sir.
Excellent. Please go ahead. We can hear you well.
Thank you, sir. My is visible.
Oh, yeah, now it's there. Excellent. Go ahead.
Yeah. So good evening to one and all present here in this conference, day 5. Today I am here to talk our work which we have submitted in HASOC 2020, and the title is Identifying Offensive Content in Indo-European Languages. The co-authors of this work are Ankit Kumar Mishra, myself, Sunil Soumya, and Abhinav Kumar. Okay, so what is the motivation of this research work was? Let me just give some lights on that one. That social media is one of the essential components that we all know. And the primary objective why the social media was designed, according to me, was just for the communication, so that it can make our communication easier. We can communicate with any other person, anywhere, if we are anywhere in the world. But the other purpose is what the social media is fulfilling nowadays, that for any kind of marketing, for any management, like for some government agency also, like some disaster management and all, there also the social media plays a very important role. But higher accessibility of social media content requires to handle them effectively. That is also a fact, because all available contents on the social media are not clean or friendly. We can say that, right? And such unfriendly content we can term as the hate and offensive content. So this is the motivation, we can say, that why this task was proposed, and why we all did some sort of experiment, and we submitted the model, and now we have also submitted the paper, so that we can get the best model such that we can at least minimize these offensive contents which is floating throughout the social media. Okay, so there were two tasks, as it was explained by almost all the participants, like subtask A, subtask B, and there were 3 different languages. So there were in total six tasks were there. So in the subtask A, in every language, it was a classification problem. Every post, and their post was the Twitter post, has to convert, has to classify into the HOF and not. And in task B, if it is a HOF from task A, it has to be converted, classified into the hate, offensive, and profane. So that was the task for 3 different languages. And this is the data description, that from the English, we had total around 4,522 tasks, and this is the, for the training, it had around 1856 for the HOF and 1852 for the train. So almost the number of data was balanced. But for the Hindi, as you can see that the number of training data was only 847 for the class HOF, and for NOT it was around 2,116. The class was imbalanced. The data was imbalanced, right? And for the German also, we see the similar pattern. The data was imbalanced. And this development data here refers with which we validated our data, or we can say the test data. We had given the name as development data. And there was one more data, which was the private data with which the organizer tested, and finally they gave the ranking for the different models submitted. Similarly, for task B, for 3 different languages, this was the data description. And there also we can see that we had, for training in hate 158, and then here almost double in the case of the offense 321. And then in the profane, we had even more data, like 1,377. So again, the data imbalance we can see here. 234, 456, 148, and like that we had for different cases. This was the data statistics. Fine. So what we did, that once we received the data, we did some pre-processing, right, as it was required. So we first converted all the text into its lowercase. All punctuation were removed, numbers were removed, URLs were also removed. We did some other experiment also, some other time, the punctuation and the numbers, but it did not have any much impact, so we removed, right? So in other experiments, emojis were also removed. The clean text were then tokenized and encoded into sequence of token indexes, as it was necessary, because if we want to process the text, we need to convert into some form of the numbers that we did through these steps of encoding. And then finally, we did the padding, because every sentence length or every text length was different. And if we are building any neural network models or any machine learning model, we have to give equal lengths of input. That's why we did the padding here. And this was the classification steps, what we followed, that after reading the data, the pre-processing steps, what we just now we had seen. Then we did the preparing the embedding input. So this part was optional. So when we use the deep learning models, then we had this layer after the data pre-processing. The first layer was the embedding layer, where we converted our actual inputs into the embedded input. Right. And why we did it? Because the actual inputs was in the form of vectors, and that vectors was in the had the dimension of our vocabulary size, which was around 14,000 words in my vocabulary. So, and that was a one hot vector. So a vector for a particular word, we had one vector of means one hot vector, where one value was 1, corresponding to that index number, and all other values were 0. So that vector was completely sparse vector with all zeros except 1. So what we did, we kept an embedding layer in between, so that we can convert the high dimensional sparse vector into the low dimensional dense vectors. That was the point of having this embedding layer in between. And then that embedded input was given to the models, different models, with which we did the experiments. We created those models, then we trained those models. And after the training, again, we read the test data. We performed the same pre-processing as we did in the training case. Then we did the model prediction, and finally the classification report was, stored. And different models here, the model creation in this part, we experimented with different ML and DL models. Like in ML, we did the experiment with the linear logistic regression, and the random forest. And we did with the Svm also, we did with the gradient boosting also. So we experiment with the different machine learning models. And in the DL, we experimented with the CNN, LSTM, BiLSTM, and we also did some hybrid deep models. And this was our best model for the English data set. And that's why we were showing this one. And how the input was given, because we were using the LSTM model. So the input was given in the timestamp manner, first of all. And then every input, suppose so in the particular text, the first word and every word exactly. So it was first represented in the vocabulary size, which was 11,848 in the case of English, where so a vector, one hot vector of this many dimension. So see, all the values are 0 except 1, 1. So what we did, we converted into the embedded vectors, where we had the 300 dimensional vector, but all the values were, when there was no zeros, for every position we had some values, right? So we converted the high dimensional sparse vector into the low dimensional dense values vectors. And that input was given to the LSTM, where we used 256 neurons. And every input like that we passed at a different timestamp. Here we got the complete representation of our post, the text Twitter post, right? And whatever the representation we got here, that was given to the first dense layer, where we used the 16 different neurons, and that vector was given to the finally the output layer, where we got the 2 different probability of this post having the class of not or having the class of Hoff, where we use the the softmax activation function here at the output layer, and that give us the final class value. So this was the different hyperparameters that for whenever I use the DL model, we also use the embedding layer in between. So we used different embedding, the pre-trained embedding models from the globe or word to wake, or sometimes we also use the random embedding. But as I'm talking about our best model, so their LSTM with the globe with 300 dimension gave the best results. So that was the first hyperparameters what we used. Then 256 neuron in the LSTM units. The one dense layer we used after the LSTM. There we use the activation function as ReLU, and at the output layer we use the activation function as softmax. The optimizer was Atom. The learning rate was 0.001. We trained for 50 epochs with 16 batch size. So coming to the result part for the English data set. So these are the results, the best results I am reporting here. So for the subtask A, these were the models which performed relatively better than the other models. So for the CNN, with the globe embedding, so we got 0.85 on the development data set. The best model was this LSTM with the globe, which reported around 0.86 macro F1 score value. Hybrid also with the word to vec embedding, we got 0.83 macro F1 score. So this was the best model for the English subtask A. Similarly, for the subtask B, so these were the various model with which we tried. We tried with other models also, but we have included this because relatively they had the better performance. And the best model for the subtask B for the English data set was again the LSTM with the globe embedding, where we reported around 0.55 macro F1 score for the development data set. Similarly, for the Hindi data set, again, for the subtask A, we got the best model as CNN with random embedding. So we tried with the globe also, we tried with the, word to vec also, but surprisingly, the random embedding performed better for the Hindi data set. Why? Because for the, we could not try with the globe here, because globe is not available for the Hindi data set. We made our own embeddings for the word to vec, but the word to vec did not perform well here in this case. So random embedding performed well. where the weights between the input and the embedding layer was completely random, and then we trained our weight during the training process, and we obtained 0.67 macro F1 score. And for subtask B, again the CNN with random embedding performed best with 0.42 F1 score. For the German data set, for the subtask A, the machine learning model, random forest, the ensemble model, it performed well with the TF-IDF vector. When we gave the input with as a TF-IDF vector, that time it reported 0.78 macro F1 score. But for the subtask B, the CNN with random embedding gave the best result with 0.48 macro F1 score. So this was our results, and our best 6 models are these, which we reported in the paper. And for the English subtask A, as you can see that for the development macro score, F1 score was 0.86, but the test macro F1 score, which this accuracy was given by the organizers for the private data set, which was 0.5152, and our model was identified as the best model, and it got the first rank in the competition for the English subtask A. For the English subtask subtask B, we obtained the 17th rank. Similarly, for the Hindi subtask A, these are the 11th and 9th for subtask B, and similarly for the German data set, the ranks are given in the table. So finally, the conclusion, initially we visualize the data, and accordingly we perform the pre-processing steps. And then we experimented with various MLMDL models, like for the ML case, SVM, LR, random forest. And for the DL, we deep learning models, based models like CNN, LSTM, hybrid models. So we also tried with the BiLSTMs. And then in the DL, wherever we use the DL based models, there we tried with the different embeddings also, like globe, word2vec, or random for random embedding. Right, and the best model what we got and for English subtask A, where we got the first rank, was LSTM with globe embedding. Okay, so that's all. So thank you so much to the organizer for the chance to participate in the competition, and thank you all for everything. Thank you. Yeah, that's all for my side.
Oh, excellent. Thank you, Sunil. And of course, congratulations for the very good performance in English. Yeah. We have seen now from all participants almost that, I think from all, that the scores on the first test set, the development set, are much higher than on the private test set, the final decision. The previous scores are in the 80s, even beyond the HASOC 2019, and then the private data is much lower, so there is some issue there, definitely. Just a quick question on the random embedding. That is, so that's really fully randomly assigned a vector to each word, and that is not changed during training.
No, sir. It was randomly assigned initially, and it was changed during training. It was like it was changing for every epoch or for every batch size. Then it was changing. So that was the thing for the random embedding.
Okay. So it's almost like creating your own word embeddings based from a random,
yes,
random starting point.
Yes.
Okay. Oh, but very good to see the again worker. This is a good, seems to be a good workaround. So there is no glove for Hindi. Okay, I've forgotten that. Should be. No?
Yeah, definitely, sir. We have to work hard because as some other participant, they have also pointed out that it was a code mixed data, and I guess because we did not have the globe embedding, like globe is only for the English data set. We tried with the word2vec, but I don't know, it did not perform well. So we have to try with other embeddings like BERT if it is possible, or fast text, and that we have to do in the future.
No. Excellent. And of course, other code mixes is a different challenge.
Yes.
So very nice work again. Thank you very much. Any other questions? Nice, Sunil. Then thank you again. And we move to the next talk, which could be from Jin UK. Is there a recording from Jin UK?
Yeah, there is a recording. Yeah.
Thank you.
Very nice. Thank you. And we move to the next recording. So Suru will just...
Yeah, so let me share my screen again.
Hello, everyone. It's a great honor to present my work at the meeting. My paper topic is Simon et al. 2020, Detecting Hate Speech and Offensive Content in German Language with BERT and Ensembles.
Could you switch to the video, please? Just the audio is there now.
Yeah, I think I had just shared my screen. Just give me a moment.
Sure, sure. That's always a changing, and these technical issues are never so easy as they look. Yeah.
Hello,
We could hear the video.
Are you able to see it now?
No, I just see the video.
Yeah.
I don't see the video. I just hear the audio.
Oh, okay. That's strange.
Oh,
I think you share a folder that SPC with us. Share a video.
I have shared it. Just let me see if there are any more options.
we see your screen, but it's not
Share sound optimize.
video.
Okay, it should have been visible.
First,
Okay, I actually shared everything right now.
Now we see your Explorer, Windows Explorer. We can see.
Okay, but
and
not
we heard. Now we heard the video. We heard the sound.
That
sometimes.
Okay, I think this now.
There is it now. Yes, now we have
great.
it.
Okay, so let me start.
Okay. Thank you. Excellent.
And offensive content in German language with BERT and Ensembles. Below, I will introduce my work in 3 parts. The first part introduces the background information of the mission, and the second part explains the methods of and data processing I used in the competition. The third part is to share the specific details and results of the experiment. Okay, let's start with the first part. The mission is primarily a test for offensive language. The importance of detecting offensive language is becoming more and more important in today's society. With the rapid development of the network information technology, we are more and more used to express our opinions and social media such as Facebook, Twitter, and so on. But there is a lot of hate speech and offensive language in those published contents. Hate speech is published in cyberspace and spread through the network media, aiming at groups with specific identities to carry out offensive and harmful speech. The governance of network hate speech has gradually attracted people's attention. Nowadays, such social media companies are studying the identification of hate speech and offensive language, which is very difficult because some sentences containing literal words are difficult to detect as hate words, but these sentences may cause mental harm to individuals or certain groups. Studies have shown that The spread of obscene language on the internet will cause some people's psychological problems, leading to depression and other psychological diseases, and even make people commit suicide. So, this mission is very necessary. Here are the details of the mission. There are two subtasks. Subtask A is the binary task. Subtask B is the multi-category task. My model and data processing are described below. I organized the data into three aspects. Firstly, detecting punctuation and measure of space. Detect URLs. Finally, using words instead of emotions. We replaced the laughing expression with laughter and the crying expression with crying. This is the model I used. This model is mainly to feature BERT. The output of BERT GR is processed. We also show that BERT's intermediate layer encode a rich layer of linguistic information with the surface features and the bottom. Syntactic features in the middle and thematic features at the top. In order to obtain rich thematic features, we made some adjustments to BERT's superstructure. It describes the model in more detail. P_O is the poor output, thus the hidden state is the sequence of hidden states at the out of the last layer of the BERT GR model. H_N is the second output returned by BIGR, and HAVG is the original pruning of the BIGRU output. Hmax is the max pruning of BIGR output. In this model, we first getting the sequence of hidden states and the output of the last layer of BERT GR. Secondly, we input the last hidden state into BILSTM and BIGRU to get the output of BIGRU and the hidden state of BIGRU-HN. Thirdly, getting the HAVG by average pruning and the Hmax by max pruning. After getting the output of BIGRU, finally Hmax, HAVG, and HN and PO into the classifier and experiment procedures are described below. First, we get the new validation set and new training set by using the stratified 5-fold cross validation. Secondly, in each fold of the dataset, we choose the model with the highest FE score in the validation set to predict the test set, and we get the prediction results of model by averaging the probability of the 5 prediction results. Thirdly, we input data into 1 to 4 models of training with the training set and predict 1 to 4 results with the test set. Finally, we get the final result by combining the 4 results by hard voting. This is the higher parameters of each subtask. We have come to this conclusion about the competition. The paper introduces the model and the final results of Simon team in hate speech and offensive content identification in Indo-European languages. The model uses BERT-GER, BI-GRU, BI-LSTM, and so on, which improves the ability of the model to obtain semantic information features. The identification of hate speech and offensive content in social media has a positive effect on the development of society. Okay, that's all. Thanks for listening.
So, thank you. So, all worked fine now, and it's good that the participants could send their presentations. At least we can see their approaches. So we move on to the next talk, and I see already in the participant list Etzike Tohukwu. Please share your screen and please go ahead.
All right. Can you see my screen?
Not yet, but I think it's coming. Voice is very nice, but we cannot yet see this presentation.
Can you see it now?
I cannot.
Wow. What's happening?
Host. Oh, don't worry. Try. Maybe give it another try.
Okay. Can you see it now?
Yes, there we are. Excellent.
Okay.
Now it's there. Perfect. Thank you. And please go ahead.
Yeah. All right. So hello all. I'm going to be presenting our work on the HACCP competition, the subtrack of FIRE 2020, titled Bet Fine-Tuning for the Identification of Hate Speech and Offensive Languages in Tweets. Yeah, so this work was jointly done by myself and my teammates, Monica and Vanessa. Yeah, and I'm representing both of us. All right. So, as you all know, recent years have seen massive increase in the use of internet services across different sectors. Of paramount importance is its use in the social media space. Yeah, and we all know that there has been a rise in the propagation of hateful and offensive comments on these platforms, which is a great deviation from what they were initially intended for. Yeah, so the aim of this HACCP track is to correctly identify and flag these hateful and derogatory comments on Twitter data. Yeah. So let's go to the dataset description. Yeah. The entire corpus given for the English language task contained 3,708 tweets. Subtask A is a binary classification task. We are asked to classify the tweets into two categories: hate offensive and non-hate offensive. And in the data set, there's an equal distribution, almost equal distribution in the subtask A. On subtask B, on the other hand, we have a highly imbalanced data set. The four classes, non, profane, offensive, and hate, are highly imbalanced, with none having the most data. All right, so let's look at the proposed system. In our proposed system, we just have a system whereby the tweet enters the preprocessing block. From the preprocessing block, it enters our BERT model, because we use BERT as our final system. Then we put it into a concat pool, and then softmax, and then from there we get our classes. So let's look at the system in detail. We use two deep learning architectures for our experiments. We conducted two experiments with two different architectures. Sorry, we conducted three experiments with two different architectures. We used the ULM fits for the first experiment in the two tasks. Then we used the monolingual BERT-based on-case transformer model. Yeah, for the first experiment, experiment 2.1, we used the mean pool classification head. And in experiment 2.2, we used a concat pool classification head, that is a mean and a mean concatenated with a max pool, the classification. So let's look at the model description, the visual representation. So this is the visual representation. We can see our inputs gets into the transformer, then all our hidden features are passed into the mean pool and max pool block and concatenated together. From there, it enters a fully connected linear layer, then softmax, and then our outputs. All right. So let's look at our system in detail. For subtask A, the only preprocessing done was tokenization. We use the appropriate tokenizer for each of the experiments. For the ULM fit, we use the appropriate support tokenizer. Then for BERT, we used the appropriate retrain BERT tokens. The text in each of the experiments, the tokens in each of the subtasks, we are truncated to 128 tokens. This was done to limit memory consumption if there was, in case of any. In subtask B, however, due to the high imbalance we've already seen, we upsample the data by resampling the minority classes to match the number of majority classes. And we did this by using the class balance sampler from Catalyst, yeah, whereby a weighted sampling is done so that all the classes will have an equal distribution. All right, let's look at the model training details. The details of the training are here. All the trainings were done on a P100 GPU. Adam optimizer with weight decay was used for both tasks, with learning rates sets with a decreasing linear schedule across both tasks, both subtasks. And for the first subtask, we started with a maximum learning rate of 1 in 5. For the second subtask, we had a maximum learning rate of 1 in 4. All right. All of the models were trained for 6 epochs in both tasks, and all the layers in the models were made trainable. So the weights were adjusted in all the layers during the training. There was no progressive unfreezing. Then our validation and assembling strategies. Our validation strategy was a stratified key-fold split across 5 folds. The individual models were trained on each of those splits, and then they were aggregated by a simple mean across all the outputs, all the output probabilities, and we use that to get our final ensemble. All right, so the results, as you can see from the results, our BERT model with the concat pool got the highest scores on the local validations, which was what we submitted, and on the test CV was also very good because for the subtask A, it placed us in 24th place, but the difference between our model and the highest model wasn't so much, about 0.02. Then for the subtask B, we are placed in first place. Yeah. So as you can see, the major difference being this concat pool that we use, because the concat pool basically learns, it aggregates all the hidden features both across the mean and across the max dimension. So you have like a very, very rich feature embedding, which is past the linear, layer. So our conclusion, we have presented a unique end-to-end approach for fine-tuning a BERT transformer for the detection and flagging of hate speech on Twitter datasets. We didn't use any external data for our experiments, and for further work, we could use more generalizable transformer models, more extensive ones like Roberta or Alberta to improve score. So, and we could also use additional data to append to the ones we already have, just to make the model have more data to learn from and improve the score. Yeah. So thank you to the all our codes for the experiments can be found on this. We've open sourced it on this link. Yeah. So thank you to the organizers of the FIRE 2020 and the HASL competition. And then thank you all for listening for the time. So if there are any questions, please, or suggestions, feel free to ask. Thank you.
Oh, great. Thank you very much. Very interesting to see label smoothing as a technique here. I think nobody else has mentioned that. And the use of external resources. I think it's very, very good. We haven't seen also a lot of work on that. Even though HASOC 2019 data was there, it seems that nobody has really used it so much.
Yeah. We didn't use it.
Did you? You didn't? You didn't try it? Okay.
No, we didn't try it. So.
Yeah, we have to do some post experiments to see if it is valuable.
Yes.
Do you think that really Albert and Roberta would be helpful for your performance?
Yeah, I feel it's like my thoughts, because they have like they are better state of the art on classification tags. So I feel that it is just like an intuition that maybe if you put a Roberta model there, it may perform better. Yeah, I didn't get to try it, but it's something I will do later. Yeah.
Great. Thank you so much, Sean. Nice presentation. We got good insight on what you did. And you were a transcontinental team, so please help us to promote the task again in Africa and in Canada. So we will be happy to see more participants.
Yeah, thank you.
Thank you so much for joining. And we move on then to the next presentation. Thank you, Junyi Lee. I think she has not sent presentation.
Yeah, she has there's a presentation. Yeah, there's a recorded video again. Yeah.
Then I didn't see it on your list. Sorry about that, my confusion. Then we can.
I'm sharing my screen again.
Okay. So we'll see a recorded presentation because of issues with the presentation possibilities from China, but we are glad that we can see this.
Everyone.
Yeah. Are you able to see my screen now?
Excellent. Perfect. It's fine. It's fine.
All right. So let me just play it. Give me 1 second.
Very good.
Can you hear me? Okay. I'm honored to represent our team in this online conference. Now, you can see my paper title. I will share my paper, AI BERT-based marks ensemble with self-training for identifying hate speech and offensive content in Indo-European languages. From the content, I will share our work for 5 terms. Its content: introduction, data, methods, results, and conclusions. First part is introduction. That is the introduction part. In this part, I will briefly introduce the task background and the subtask involved. In recent years, due to the rapid development of the mobile internet and social media platforms, people have begun to use various social media to share their lives, such as Facebook or Twitter. People share their view on life on social media, and this behavior may receive good or bad comments. Some bad comments slowly evolved into offensive language. Social media is flooded with a lot of offensive language, and these remarks have led to deviations in people's perceptions of things. All major social media platforms urgently need tools to automatically monitor user speech. In this task, we only join the subtask A in English. Subtask A focuses on hate speech and offensive language identification, offered for English, German, Hindi. We only join the English subtask A. The subtask A is binary classification, in which participating systems are required to classify tweeters into 2 classes, namely hate and offensive (HOF) and non-hate and offensive (NOT). Okay. Now, let's see the second term, data part. Then, I will briefly introduce the data side of subtask A in English. First, we will see the left picture. This picture shows that the number of the data sites. And the subtask A provided training data set and test data set. Containing training data set has 3,708. The test data set 814. And the blue color is represented the NOT class, and the orange color represents the HOI. So let me see the right. There have an example from the data set. The example has 3 terms: content, text, label, and ID. Okay, next. Next is methods. In this part, I will introduce my method comprehension. My method consists of AR BERT with self-training and max ensemble. First is self-training. The picture shows the self-training process. In natural language processing, using different data in the same domain to train a model is a form of model training. The training method is called self-training and aims to establish a broad thematic understanding to promote performance improvements for training and task. Our self-training method uses the idea of teacher and students. Teacher and students. Teacher and students reference to the same training process. You can see the picture, the middle. The beginning of the student training is the end of the teacher training, which can deepen the learning of the model. We use the same model in the teacher and student training. The teacher part uses an additional external dataset, which is the task dataset of Svm 2020. This is external dataset. And this dataset has same purpose as the HASOC 2020 task, but the content of the data is different. We only randomly use 10,000 sentences. The students part use the training dataset of the task. We can see the progress through the picture. Okay, next. Next is AR-BERT and Max ensemble. First, the top picture is AI-BERT progress. The AI-BERT model combines two parameter reduction technique, which eliminates of the main obstacle to scanning pre-training model. The first is decomposed embedded parameterization. This separation makes it easier to increase the heading size without significantly increasing the parameter size of the vocabulary embedding. Okay, let me see the front part. And the second technique is cross-layer parameter sharing. This technique prevents the parameters from increasing with the depth of the network. In this, the AI-BERT model performs better when the number of parameters decrease, but it can get good grades. We know next is Max ensemble. We know that the common ensemble method is based on the voting. In this paper, we filter multiple AI-BERT models with different random seeds. For each input, we will output the best prediction and probability derived from the filtered AI-BERT and summarize the predictive probability of each model. The output of the ensemble model is the prediction with the highest probability. This ensemble method is called the Max ensemble. This bottom formula is shows that the process of max ensemble. We can see this formula. Okay, that is our all methods. Next part is results. In this part, I will show the results of our team in subtask A and the results of top 4 in the leaderboard. Simply, table. The top 4 results show that 0.5152 to the 0.5048. And my result is 0.4976. Now, I will show you the final part is conclusion. Simple conclusion. In the task, when many use the AI-built model, based on the model, we also adopt the method of self-training and max ensemble. However, in the ranking, the performance of our model is still not satisfying. In the future, we will improve our methods by adjusting our model and trying more ensemble methods. That's all. Thank you.
Okay. Oh, thank you very much for sending the video. Any issues for discussion, comment? On the case, now I think we can move on. I see 2 more presentations on my list. The first would be from Ujval. Ah, yeah, I think it's already there, already liberated as a co-host. Oh, excellent. And we see the video.
Yeah, hi, can you guys hear me?
We can hear you well, yes. Let's.
Yeah, great. I'll just share my screen.
Yeah, please. Welcome. And we see, now I've seen it already. Yeah, there we go. And go ahead, please.
Great, thank you. So we titled our presentation, Leveraging Multilingual Transformers for Hate Speech Detection. I'm Ujjwal, and together with my co-authors, on behalf of them, I'll be presenting this particular work that we've did. Let's start with the introduction. So, so we start off with motivating this problem, and with recent years, there's been a tremendous rise in social media usage across the board. And unfortunately, with this, there's also been an increase in toxicity and hateful content online. So detecting this type of hateful and offensive content in most comments and posts is an important task, and detecting this is the first step to sort of take steps which can handle and counteract this behavior. So what are the major challenges with this type of detecting hate speech? Well, existing NLP researchers are not well suited for detecting social media content because the style of the text vastly varies, and existing NLP techniques use wikidumps, which are all well-structured and well-written texts, whereas social media typically do not operate within the bounds of the grammar that we know. Social media posts also frequently use abbreviations and variety of various spellings, which are not observed in the general domain. Pragmatics also plays a crucial role when words cannot be taken in the literal sense, as sarcasm and its variants are predominant in social media. So here's a quick overview. I'm sure everybody's already talked about this, but just to make this complete, there are around 4,000 sentences for English and roughly around 3,000 for German and Hindi. So in this test, we're talking about the validation split, and this is not the private test data. And all the results we're talking about in this presentation will be in reference to this split that we've made on the given data. And this is not the private data that our code was later tested on. So there are two tasks in the HASOP track, coarse grained and fine grained, where in the fine grained we divide hateful content into hateful, offensive, and profane. Again, for task-wise distribution, just to make the slides complete, we have this distribution. Moving on with methodology, as talked about earlier, preprocessing is an important step and can make or break a model. So we tokenize our data and we segment the hashtags present in all the tweets. We also take other data such as dates, emojis, mentions, and links, and we sort of remove it also from the text. We also clean up certain reserved words such as at rate RT, which means retweet, and we clean up the data. So we broadly have three major embeddings in our model. One is we would like to generate semantic representations for the emojis used in the tweet. So using social media ourselves, we know that emojis are often used to denote sarcasm. And a smiley emoji may not always mean a smile, but can have a lot of other meanings as well. So we'd sort of like to capture this semantic. So we opt not to directly use the textual form of the emojis, but embed this emoji into a vector space using emoji to vec. We also used pre-trained transform models such as Xlm Robot to generate embeddings for the segmented hashtags in a methodology similar to the way done by Universal Sentence Encoder. We also take the clean text obtained from the tweet in the pre-processing step we talked about earlier, and then we sort of fine-tune it with that transform model, and all these three are used to classify later on. So for the training, as we talked about, we pass them to a two-layer, multi-layer perceptron, all these three embeddings concatenated together, and we generate the label. The loss from the classifier is propagated back to the transformer, and we sort of fine-tune the transformer this way. We also experiment with using different learning rates and optimization methods. And one of the things we found useful was to use adaptive learning rates based on the validation macro F1 score. Other than all of this, we also experiment with different variants of transformers and BERT-based models, such as multilingual BERT, digital BERT, Albert, and Xlm Robot. And we find that Xlm Robot provided the best results for the task. I've always found that a dry run with the data is useful when trying to understand a model. So here's a quick dry run. So we have the raw text tweet, and cleaning up, we separate out the emojis, the clean text, and hashtags. We then segment the hashtags and pass them to a static transformer, which is just a pre-trained transformer, which we don't modify at all. Emoji to vec is a way to map emojis into vector spaces. So we use that to generate embeddings for the emojis. And using a transform encoder, we sort of concatenate them, all of them, and pass them to a two-layer MLP. This loss is again backpropagated, and we sort of iterate this until we get a predicted label. Okay, moving on to the results. We observe that fine-tuning a model helps across the board in all the three languages. Here, when we say freeze, we mean not backpropagating the loss and just using the pre-trained transformer directly. Adaptive is using adaptive learning rate, and tuned is using a standard way of using just an Adam optimizer with early stopping. So here we observe that in some cases adaptive helps, and in other cases adaptive doesn't, and using Adam optimizer with early stopping is actually the best way forward. We also perform a series of ablation experiments, and what we notice is that while monolingual is sometimes better, multilingual leads to a tremendous boost in the F1 scores. But in the cases where it does not lead to a boost, it leads to a minute drop. So it may be in an industrial setting where you would sort of have to cater to a larger variety of languages. Maybe multilingual setting is actually a reasonable trade-off where you can expect some significant boosts, but the trade-offs are minor and in most cases and in real-world scenarios actually negligible. So in Hindi and English, we notice that monolingual performances are better, but in German, we notice that the multilingual is better and by a significant bit. Sort of moving on. So we also we're slightly curious to see how our model sort of performs against the industry standard. So Perspective API is this methodology developed in collaboration with the Google Content Abuse team and Jigsaw, and it's been widely used in a variety of spaces such as Discuss and the New York Times. And they sort of use machine learning models to estimate various metrics and to sort of model the impact this particular comment has in a conversation. They have a variety of fields such as toxicity, severe toxicity, and so forth. And in English, I believe they have around 9 fields, whereas in German, they only have 6, with fields such as sexually explicit and obscene not being present in the German language variant of the API. So when we say monolingual and multilingual over here, Monolingual is using only that particular language, and in multilingual, we train English and German combined, where we drop off the additional fields such as sexually explicit and obscene fields in English, and we only use those sets which are common for both English and German. One interesting observation we see is that in the coarse-grained category, the results are comparable to the results we got with our BERT-based models. But in the finer-grained categories, our models significantly outperform using just the Perspective APIs. So, so before I sort of move on, the way we went about using Perspective API also was the API gives you a value, thinking how the probability of this being toxic or not, the probability of this comment being explicit or not. And we use these as a input for our two-layer multi-layer perceptron, same as the one we used for BERT. So yeah, this was the experiment with Perspective API. And concluding, we showcase that there's multilingual transformers are significantly useful, and we can sort of leverage this potential with them to sort of identify hateful content online. Hashtags are important, and we cannot neglect them. And with the ablation experiments, we also find that emojis add significant value to the classification head. Multilingual models also perform better than the monolingual models for low or moderate resource languages. And in the absence of better data or better models outline, we can sort of leverage multilingual models to do the classification. In case of any questions, you can sort of email us at firstname, lastname at research.tripleit.ac.in, and this is our presentation. Thank you.
Ujjwal, again, thank you very much. Nice work. Very nice that we see the effect of the pre-processing. Not all participants have shown this effect, and you showed it very nice in the results. How was is the effect of dropping emojis and so on. Also very interesting to compare to the Google system. And again, we see that for you, the performance for English is much higher than for the other two languages, at least in the test data there. So again, we have seen this several times. So simply the quality of the models are better for English, right? What do you think?
Yeah, I think because English is much more widely used. The data for English where the transform models are trained are also significantly higher, orders of magnitude higher than the ones for, say, German and Hindi. So the models' weights are much better tuned, and therefore I think we get much better results for English.
Also, there is still some room for improvement with the multilingual issues. Again, thank you very much. Great work.
Thank you.
And then any questions here from the people present? If not, I think we move on to Biswarup.
Hi.
Hi, we hear you.
Yes, I'll just share my screen in a minute.
Excellent, we can hear you well.
Yes. Is it visible?
It's coming up. Let's see. Yes. Oh, yes, this is here now.
Yes.
Go ahead.
Thank you for giving me the last spot, actually, because I could hear everyone's knowledge and understanding about the topic and could hear a lot of approaches for that. So thank you for giving me this spot. And so I'm here to represent my college, Jadavpur University, and we had made a model based on a deep learning with Roberta and random forest for hate speech and offensive content identification in Indo-European languages. And me and my colleague, actually my senior, Abhishek Gorain, we had made this project into life. And so first, the aim and motivation part, which everyone has spoken about, that this task was basically divided into two subtasks of hate speech, hate and offensive classifications. So first was the binary classification task, and then a 3-class variation of the hate speech. So what we have used is a pre-trained multilingual model, Roberta, as the base for the contextual word representation for the 2-class sentiment analysis task. And then from that model, we have further classified into 3 classes by a random forest classifier using different textual features as input features. And you'll see that the input features are rather new in knowledge. And so the data, we have used a ratio of 80% and 80:20 for the training and validation purposes. And first, for the methodology, we did the pre-processing task first, so which are normally the same for everyone, which is replacing emojis and emoticons, removing mentions, removing URLs, contracting the white spaces, extracting words from hashtags, and normalizing the pseudonym. So the so this is a basic methodology of the task. First, there's the pre-processing task. Then there's the Roberta model, pre-trained Roberta model, which is a multilingual model, and which we have used the same model for all the three tasks. So which it makes it the task very scalable. So which gives the output of the binary labels, and which is the subtask one output. And then from the Roberta model, we get embeddings, and we get word vec embeddings and different features, textual features, which I'll show in a minute. So for that, we use feature selection of random forest for the importance ranking, and then use the random forest classifier upon that. So for the task one outputs for the hate, we have defined the Hoffire's i.e. the hateful offensive languages into three different various labels of the hate, offensive, and profane. So aligned with the results from the Roberta model, and then the subtask 2 output. So first, the Roberta model, we have used the Hugging Face Team Transformer library for the pre-trained Roberta model, which has been trained on 100 different languages. But as mentioned by everyone, it performs well for English because it has a huge amount of training done on the English language in the English datasets. So which was the Roberta BERT base architecture, which is 12 layers, 768 hidden, and 12 heads and 125 M parameters of. We have trained it for 10 epochs, and the batch size has been set to be 32. So for the random forest model, which is more interesting for us, we have extracted different textual features for it. So first was the Roberta embeddings, which were from this model itself. We have used along with the word-to-vec embeddings, and then we have used TF-IDF. We have used normalized counts of words with positive, negative, and neutral sentiments in the corresponding languages. Normalized frequency of auxiliary verbs were also done. Subjectivity score of the text was done, which was calculated using predefined libraries. And the features, all these features which were extracted, were then put into a feature importance ranking, and then only those with higher feature importance were added to the training of the Roberta model. And due to the fact that there was an imbalance in class, we have used weights to balance the classes, i.e. which uses the values of labels to adjust weights as inversely proportional to class frequencies in the data. And this is a very commonly used method, so we have used it to balance the classes. Our results were quite satisfactory, not too good. For the English task, we have produced good results for the subtask A. For B, we have got rather not very satisfactory results. For the other languages too, we have got very not so good results. So the results for the task B were not up to the mark, which might be due to the absence of high quantities of data for the same. And the other result languages were votes, as mentioned by everyone, that for English languages, the results are the best. For us also, we have resulted the same. And this major reason could be the class imbalance. And the class imbalance, we tried to fix it up with a good method, with a knowledgeable method, but far better methodology could be used to solve it. And considering previous approaches, the conclusions are that our approach is comparatively different because we have used a totally different architecture and a methodology of feature extraction, which I think is a newer process. And we have used both the Roberta vectors and word-to-vec embeddings to, along with various other textual features for the random forest model. And it is a very generalized and versatile framework. And in the future work, we'll further fine tune the classification models and try to increase the performance, and we'll see upon the better methodologies of the class imbalance task. So these are some of the references, and thank everyone. I thank to the for hosting such a beautiful task and for giving me this opportunity to represent. Thank you. And if you have any doubt, you could mail me or my colleague in this email ID provided. Thank you.
Great, thank you, Biswarup. Also good description of what has been done, very nice. And we see our random forest classifier. Again,
yes,
we see a very different approach here, yeah, that's true. And yeah, and again, lots of pre-processing and so on. And interesting that also a feature selection model has performed quite
Yes,
okay
our
still.
main task was to actually experiment with the textual features. So we have tried different textual features which were new to us too. So tried on with that and tried to get good results based on that.
Oh, excellent. That is very nice to see a variety of results, and overall we've seen that people use the models that are there available and well known, but they integrate it in different forms, or they use something quite innovative like here. And yeah, so any other questions from the audience? Not the case. So
okay, thank you.
Thank you very much for presentation. It's very clear. And we've seen now very interesting work. So after this concludes our HASOC session. So again, thank all the participants for staying out here on a Sunday and doing your presentations. Stay with us and also have a look at the HASOC 2019 data and check whether your approaches work there. And we will also work on the issues of how is the test data, private test data related to the results that we got finally. So there's a big drop and we have to investigate that. But that gives a lot of room for all of us for future work. So again, thank you very much for your valuable time and your great contributions and all the coding that was done. And HASOC might continue, I hope, I think. We are very positive that we will continue another year. So please join us again and let us see how far we can get. Then again, thanks to Suru, the main organizer here of this session. Everything went very smoothly, I think, so we could benefit. And there's also people still on the YouTube, so both channels work well. Thank you.
Yep.
Goodbye
Thank you.
then.
Thank you, Thomas. All right. So we now take a 5 minutes break, and when we return, we start with the EDNIL track presentations, which will be chaired by Bhargav. All right, Bhargav, let's begin then. Okay, so I hand over now to Bhargav. He will. So we now next have the EDNIL track presentations, and Bhargav will be chairing the session. So I hand over to Bhargav.
First, I want to invite Subhanshu Mishra. Subhanshu, please share your screen.
Yes, just give me a second. Okay. Can everyone see my screen?
Yes.
And can you see my presentation also?
Yes.
Okay, I'm just going to put it on full screen mode. It's available, right?
Yes.
Okay, great. So I can start.
Yes.
Go ahead. Okay, thank you. So thanks everyone for organizing this very interesting competition on event detection from news in Indian languages, EDNIL. I'm presenting my work on non-neural structure prediction for event detection for news in Indian languages. The title is very specifically chosen because I did not use a neural network approach. So, but at the same time, like it works very well, and that's the thing I want to highlight from this presentation. So the team name was 3 Idiots. All the code is already available and it is open source. So you can go to this link and you can see what the code is. So to give an overview of our approach, basically I participated in both the tasks and the key idea is and as I'm going to detail in the later part of the presentation is basically both the task submission were actually predicted using a single model. But I did not do any multitask learning as such. It's just like a simple way of transforming both the tasks so that they can be solved by a single model. Then another key highlight was that the original data was in XML format, and if you convert that data into the right format, then you can use all these transformations. Now coming to the non-neural part, which was I think the thing I spent the least amount of time was I just used the very basic traditional architecture for solving sequence tagging problems, which is just n-gram plus some sort of regex features. I'm going to talk about those later. And then I post-process the scores or post-process the predictions of the model for each subtask and then do the submission for each of the subtasks independently. Now, the good thing is the submission, they were had the best performance across all languages on both the tasks. So this was a very big win, also surprising for me. And it from what I read, I think in the opening presentation of FIRE, is like some of the other models which you use, they use some neural network architecture. So yes, I'm happy that it was able to improve on those scores. As I'm going to show you, it's a very easy to implement, very fast to train, and very fast to perform inference. It's finishes in around 4 minutes. So for each language, doing the prediction and training took around 4 to 5 minutes. So effectively in an hour, I was able to make the submission for all languages. So I'll not delve too much on this, but because I'm the first presenter, let me talk a bit about what the task was. So the goal is you are given a span of text, and then you have to identify events in that text, and you have to identify some event frames. These were the two tasks. And the first task is only related to, okay, what type of event is there in the task and where that event's representation occurs. And the second one is what are the properties of that event. So let me give it to you from show it to you using an example. So this is a text which was given to us. And the first task actually just had okay, is it a man-made event or I think a natural event? And what is the span which is related to this event? So here in this case, these are all the spans which indicate that it's a man-made event, like explosion, blast, so on. For subtask 2, the same text. Now you have additional attributes, like because for an event, you need to define the event based on how many casualties were there, where it happened, and what time it happened, and so on. So again, like you now have to predict like basically all these additional properties, and the output needs to be in XML format. So like effectively, you have to fill the slots on that XML template. And the way I approach this task is like you can have a single model and you can have the same approach for all languages. Same approach for all the languages. That means, and this is I did it for simplicity. Like you can of course have more advanced approaches for each of the language. And this is all the code. Like so, I mean, of course, there's slight abstraction here, but like this is all the code I use to make the submission across all the languages and all the tasks. So like the create file actually just post-processes the data set, the output data, and creates 2 files, one for each task, which I just submitted to the run. And I think I only submitted 1 run for each task and language. So that was also very efficient. And the goal is like you basically take the XML data, convert it into this BIO sequence tagging format, run a single model, post-process the model's output for task 1, task 2, and then do the submission. That's it. So what is the post and pre-processing I was talking about? So if like the original data was actually given as an XML document, and you can convert it into a very common format for doing sequence tagging, which is like for each word in the sequence, assign a label. And like the common format is often like this, like so, like the word 1 gets the label B casualties. So I use something called a BIO tagging, and the word comma like gets I casualties, 18 gets I casualties, and so on. And everything which is not part of a span gets a label O. So I have basically like just given an example of like, how the spans will look like. So in pre-processing, I convert the original XML to BIO format. For post-processing, for subtask 1, like you have to make a prediction. Like you don't have to like tell what type of man-made event it is. You just have to tell like whether it's a man-made event or a natural event. So I just strip away this label and I return the span of what the like what this phrase is looking like. For subtask 2, like you have to remove this arg parameter, and then you have to again return what that phrase looks like and use it to fill the XML slots. And that is all I did. I think there was some noise in the data. So like I found it like if we can like normalize all the labels, that means convert all the labels in uppercase. And yeah, like then it is going to be like a simple format, which I mentioned to you earlier. So what is the model? Now this is the time thing I spent least amount of time. And of course, I think like if we iterate on it, we can get even a better model. But I basically like the feature. So condition and random field is a very common approach for solving sequence tagging tasks. And it's often used as a last layer. So instead of predicting a label for every token, you predict a label sequence for the whole sequence of input. And it takes care of the structure of the label sequence so that it agrees. Like that means a B should always be followed by an I. An I can never be preceded by an O, and so on. And the features to the model was like, I just take the identity of the lowercase token. I look at the 2 to 3 character suffixes. If it's uppercase, if it's title case, if it's a digit, if it's at the beginning of a sentence, end of sentence. And basically I concatenate this feature for every token with features, with the same set of features for the neighboring tokens, and that's it. So, and then I feed it to a CRF model, which was trained using this average perceptron algorithm. It takes around like 4 minutes per language, and like it finishes. So coming to the results, like basically the model performed like best across all the tasks and all the languages, and it was around like 15% like F1 score better than the second best team. So this is quite surprising. Again, one important thing to note is like the data set is small, but I would, for sequence tagging tasks, actually the data set size is often not just measured in the number of documents, but also in the number of tokens. So I know like for each document, like the number of tokens was large. So it is not that small either. So, but there's of course like a discrepancy across languages. So like Marathi and Tamil, they have the highest resource language for this data set for this shared task, and like I think English, Bengali, and Hindi. Hindi is I think the least. And if you look at the results, like Marathi actually performed, like my model performed worst. And but so earlier I was thinking like it's something related to a data set size, maybe something related to noise. But I'm not a Marathi or a Tamil speaker, so I will not be able to like disambiguate what the reason for those things were. And yeah, like even like Tamil, which is like the second highest resource language for this task, it's like the best performance for task 2 and the second best performance for task 1. And yeah, like from what you see here, like I think some of these features are very much biased towards English, because like you don't see like uppercasing in other languages. Like I don't know like how 2 to 3 character suffixes and prefixes work in other languages. So yeah, that may also be a reason why the model performs worse than like say English. So English usually like a pretty good like score across all languages. So closing thought is basically like here's my suggestion. Like I think working on this task, like I think it around like took me 1 or 2 hours to do the whole submission. Most of it was like around organizing my code. So here, like use simple and fast baselines. Like these are very easy to implement. And the interesting thing which came out is like multitask inference is what I will call is you use a single model, but if you see there's some overlap in the task, you can actually do a lot of post-processing and get some sort of a multitask inference, which is like you can perform both the tasks using just the output of a single model. You don't even have to train the 2 tasks together, which is like much more complicated thing. And yeah, like it appears to work well than neural models, but maybe we can use like say a more principled approach using some ideas from this presentation. Yeah, that's it from my side. If you have any questions, you can contact me also at Twitter. Here's my Twitter ID, the citation of the paper. The code is already available. And I also have developed some other like more deep learning based tools for social media information extraction. So you can have a look at them at this link. Yeah. Thank you.
Any question from audience? Okay, thank you.
Thank you.
Next presentation is from Anand and his team. So Anand, please share the screen and start the presentation. Yeah. Your screen is visible.
Hi all. Okay, so today we are going to present our work for ADNL task. So ADNL is an event identification problem. So we build our solution with some deep learning based techniques. So before we dive into the session, so the short intro about us. So I am Praveen Kumar, senior research engineer. My colleagues Anand, junior research engineer, Sarafat, senior research engineer. We are all working at same organization, buddy.ai in R&D division. Yeah. Okay. So I hope you know about the objective of this problem. So the objective of this track to identify the event for a given text. EDNL, they have formalized this problem for a news article, which written in a 5 regional language. If we give some piece of text from news article, the machine has to be identified what is the event along with other entities. So in this track, there are 2 tasks. The task 1, we need to identify the event, whether it's a man-made or a natural disaster. In task 2, we need to identify the event along with other entities such that casualty, place, time, and reason. So we participated only in the English track of this challenge for the both task 1 and task 2. Yeah, so we faced a few challenges while building a model and analyzing the problem statement. Yeah, let's assume if we are asking a question to human to identify the event for the given text, it's relatively easy. But if we are asking the same question to the machine, so we need to train our machine appropriately with more data and with important features in order to achieve the better performance. So we noticed there is a challenge in the data set because it's a data set size is too small. Also, the challenge, the task to it's a different compared to the task one, because we need to identify the subtypes, those things. As I mentioned earlier. So this is our overview of our model pipeline. So we got the data from Edinal 10. So we split the data train and val, and we did ED over on the data and did a lot of feature engineering. So finally, we finalized. These three feature embeddings can be used for our architecture. Based on our internal experiments. This is our model overview. Anand, my colleague, will cover the remaining part. So why we should choose these three features and how it helps us, and also how it's really helped. Thank you. Anand, can you take over from here?
So good evening. I hope I'm audible. Right. So as my colleague Praveen mentioned, he provided a broad overview of the solution that we went along with. So before we go into a bit of depth regarding the type of embeddings that we used, a little bit about the pre-processing steps that we did. So we observed that the data was provided in the XML format with the entities already assigned to each of the tokens during the training data annotation time. So we observed that in some cases some tokens were not adequately split in this during this original process. So we tokenized them again using NLTK's word tokenizer. We also lowercase them, and we also lemmatized the tokens using NLTK's wordnet lemmatizer using its default setting, which assumes that the part of speech for a word is a noun by default. Our intention is not to normalize the words too much, which is why we stuck with the default setting as noun. So we observed that in most cases the lemmatization simply strips plurals into singular terms. So this isn't intended as a major normalization step, just as a simple pre-processing step. And apart from that, we also extracted the the part of speech tags of the tokenized words using its corresponding implementation in NLTK for the unlemmatized version of the tokens. So so on an overall perspective, our model takes 3 inputs to process and predict the required entities. So while coming up with the overall structure of the model, we decided to, while we did resort to a deep learning based approach, we also decided to go with an approach that is somewhat computationally effective. So in that regard, the first input that we use is the uncased version of Distilbert provided by the Hugging Face library to obtain word level embeddings for the tokens. So why use Distilbert when you have other options as well? Well, in the first case, this model can be fine-tuned easily on a smaller corpus to achieve good performance. It has comparatively faster inference and computational time compared to the main model. It's also parametrically much smaller than the main BERT model, while retaining most of BERT's performance on the general data sets. Apart from that, we also extract the part of speech tags as the second input for the tokens in the corpus to learn an embedding. We use this as we feel it helps better capture relations between the tokens in the sentence, and also provides useful cues for disambiguation of semantically similar classes. As a final level, we also learn character level embeddings for the tokens in the corpus as the final input. So to go into a little bit more detailed about more details regarding the architecture, we use the 3 inputs that we mentioned. The tokens after the pre-processing steps mentioned are encoded directly into the vocabulary indices based on the Distilbert's model vocabulary without splitting them into further subwords. We also retain the part of speech tags for the respective tokens, which are encoded and provided to an embedding layer. The third component involves a character level encoding of the token, which is provided to an embedding layer, which is then provided to a 1D convolutional layer and then a max pooling layer. The output of these three heads are concatenated to obtain a combined feature representation, which is finally provided to a bi-LSTM layer, and then to a fully connected layer and a final softmax layer to obtain token-wise class probabilities, as this is essentially a sequence recognition or a named entity recognition task here. Yeah, so in terms of the prediction phase, so essentially we trained separate models for the tasks for each task, but they use the same overall architecture. The only difference is in the number of output classes, or the, to be more precise, the output neurons for the final fully connected layer with the softmax activation, as this differed based on the number of classes we predicted. So for task one, we actually trained the model to predict on man-made, natural, time, place, reason, and casualties, along with the the standard classes for unknown and padding tokens. However, while we train it for these 6 classes, we only considered the predictions for man-made and natural event. For the task 2 case, we retain, in terms of classes, we retain the time, place, reason, and casualties along with the unknown and padding token classes. However, instead of the umbrella classes of man-made event and natural event, we cover all the event subtypes mentioned in the challenge overview for man-made and natural events as separate distinct classes. So in terms of, so we trained the model and we also applied mild post-processing in order to get the final output in order for the submission format. We apply the same pre-processing steps as we did for training the model and provided to the trained model for inference. We applied further steps in, so first, after we get the prediction, we group them by their output labels and convert them to the final sequence representing the token using NLT case treebank detokenizer. We also observed that we need to strip some spaces between punctuations, and we also fix some small encoding errors due to special characters. Right. So apart from that, the final evaluations for both the tasks were carried out by the EDNL team. The results were published. Yeah. So we participated only in the English language, and we came second. We did observe there is a significant difference between the first place and the second, and whatever we scored as the second place. So we kind of realized that a more simplistic approach could also pay dividends whilst also exploring a little bit more into the deep learning aspect of things. So as a conclusion, we hereby present our solution for the tasks held as part of the EDNL track. So in terms of key takeaways, we would like to explore the performance of different transformer-based models. There is some potential to explore the performance scope in that line. And another thing would be to analyze how these sort of models handle event detection from corpora from different domains compared to news articles, such as social media data, which has a more free-flowing structure and not necessarily organized as much as news articles. Right. And also in terms of final acknowledgements, we'd like to express our sincere gratitude to our office management for motivating us to participate in this competition. We also like to thank our colleagues of the R&D division of our company for their support and assistance. And yeah, these are the references. So yeah, thank you. I think with that, we conclude our presentation.
Yeah, good presentation. Any question from audience?
Hello. Yeah, I have a question. Yeah, Anand. Yeah, hi, Anand. Actually, I wanted to ask whether you have used the multilingual Distilbert that while initializing the initial weights. Did you use that?
No, we didn't use the multilingual version. We used the English version in general. Like we said, we did not participate in the other language tracks. Okay. So we started with the English version for training our model.
So did you train the language model for this? Did you train a custom language model again, or like did you just directly make use of the distilled word straight away?
Yeah, we didn't find the need to train it to start the whole training task again on a small corpus. We found it much more computationally easier to fine tune on a smaller task, which is why we actually went for the fine tuning process in the first place.
Okay, all right, okay. Thank you.
Thank you.
Any other question? So now if no, then I invite Ritesh. Ritesh, please share the screen.
Yeah, thank you, Bhargav. Okay, I hope my screen is visible and I am audible.
Yes.
Okay, should I start?
Yes.
Okay, thank you. Hi, everyone. So I'll be presenting our submission. So kind of our submissions to 3 different tracks, and I actually apologize in the beginning if the presentation is not more in the way the share task presentations had done generally. So it's kind of a more generic thing that we were looking and we were trying to explore through the data set that was made available to us through the different tracks in FHIR. And so the broader research context where it lies is thanks to Vansu actually for starting the presentation on that note. And I kind of I'll be talking about those things, but now I see that probably it would have been better if we could have experimented with the simpler models, but yeah, that's one of the things that we could probably keep in mind for the future work. So the issue that we were looking at the time of the task, and we continue to look at, is that the modern what's called the state of the art deep learning transformers based NLP, and it's the issues that come with it. So yeah, it gives good performance for most of the tasks, but there are only a handful of languages for which the pre-trained models are available. There are 104 languages for multilingual world, and there are 7,000 languages in the world. So it's just a handful of languages for which those pre-trained models are available, on which you could fine tune. There is not enough data for other languages probably to actually build those pre-trained models, and pre-training is quite expensive also, both in terms of the computational resources that are required, as well as the linguistic resources, as I said, that you need for building reasonably good models. Obviously they are not those kind of explain why we don't have these models available for a huge number of languages. And also, if you look at it, these pre-trained models that we have, they are actually trained by Google and Facebook, the huge organizations who have a lot of resources to train those, and they probably also may not have motivation to train for very small languages. Also, if they don't get the data for those languages, they will not be very interested in collecting that kind building that kind of data for training. So yeah, there are lots of issues around the whole infrastructure and the whole the way the things are moving in NLP at this point of time. Also, for a large number of tasks, we may not actually have sufficient data for fine tuning as well. And finally, there are I think there was just a workshop in EMNLP as well, Sustain NLP, and there are other forums as well where there's people are raising serious ecological concerns around training larger and larger models for NLP tasks. And along with that, there is this larger ethical concern also about democratization of technologies for vulnerable and minoritized languages and communities. So I think is, what's the solution? Where could we go? And there is no as you could see, there is no stopgap. There is no one point solution to this. There could be lots of different ways we could try and solve this. and that's where probably Shubhansu's approach would I would say is one of the solutions. So but if we really want to go ahead with deep learning and transformers, then one of the things that probably makes some sense, not I shouldn't put that as a solution, but something which could make little sense is the making use of the multilingual and transfer learning methods. So and we have a couple of models at least. So we have cross-lingual robot and we have multilingual BERT, which we could use to fine tune for say relatively less resource languages. Now, so the questions that we were addressing was what kind of data and task are these multilingual models most suitable for? I mean, if at all you could, so we really don't know in that sense that what is working with these models and what is not. So it's actually the same models that are actually, so you'll see that a lot of people in these competitions, they are using Embert and they are using Robota, and the performance is not exactly same. In some cases, they're actually not also comparable. So there are huge differences. So we don't know if it's actually the data and the design of the task that is affecting the performance. But if we make that simplistic assumption, then probably this question could be answered. Also, so if we try and maintain the performance that monolingual models give, at least in some cases, and so can we sort of approach those performance? And I was just listening to the talks in the previous track as well, the HAZOC track, and there were actually some systems which showed that multilingual models are very comparable to monolingual models, and that's what our experiments also actually showed. Okay, so the task that we participated in, EDNIL, this one, and I think you had good description of the task from the earlier two presentations, also in the task overview presentation by the organizers. So there were three, we participated in 3 languages, in the Bengali and English, just the task one, we submitted just for the task one. And also the other 2 tasks were the sentiment analysis of Dravidian languages in code mixed text. Name itself is self-explanatory. So it was a message level polarity classification. The data was from YouTube from 2 languages, Tamil and Malayalam. And HAZOC, which for which in which there were 2 subtasks. So one was, it was hate speech and offensive content identification task. So the first subtask was a binary classification task, and the other one was a 3-class classification task. And there were data from 3 languages, Hindi, English, and German. So all these 3 tasks actually had, so probably we should have participated in all the languages in EDNIL, but we were really not. We just wanted to have a look at the data and try and understand that before doing things. So that was one of the reasons why we didn't participate in all the tasks. But when we are talking about multilingual training, probably it might have been a better idea too. Yeah. Okay, so we fine-tuned 3 pre-trained models for each task. So cased multilingual BERT and multilingual distill BERT, and also XMLR, which is the cross-lingual model for Robota. Now, for each of these tasks, we use the data set from all the languages, which is what we were trying to look at. The setup for fine tuning was same across the tasks. So so language is kind of out of picture because we now have a combined data set. So we trained 1 model for each of these tasks. And so and this was what we used for each of those each of the tasks. So we're using a batch size of 12 and a learning rate of a really small learning rate actually, and we trained for 15 epochs. There was, in some cases, there was an early stopping as well because there was no improvement in the loss. So also I think that's gone under the banner. So we used Adam Optimizer for this. Now that's the scores that we finally got on these different models. And the one in the bold is actually the most efficient model. So it's the smallest one, and we did a joint training on that model. So it's a Distilbert model. So that's the smallest one that takes the least amount of time for training, and it also requires least amount of computational resource for training. And if you'll compare the performance of this model, at least the stuff that we got, the numbers that we got, it's actually across the board, it's comparable. In some cases, it's actually better than the monolingual models. So, and slightly better. So, I mean, it's just probably in the next run of the, if we'll run it again, probably the scores would be exchanged. So the differences are absolutely negligible, the 1% differences that you get. So I don't think anywhere here there is a difference of more than 1% in between the if there are other best performance and the multilingual Distilbert. So all of these numbers, they are on the test set, except for HAZOC, for which there was 15% private test set that was not released. So this is on the release test set that we had. Okay, so the measures. Okay, but if you have any questions, I'm not really discussing all the details, but probably I think I've given sufficient idea of what we did. But if there are questions that want more details, I'd be happy to answer that. So the major takeaways that we had, that is just that multilingual joint training, it does not present any specific disadvantage in terms of the performance that we got, but the gain in terms of energy consumption that we are doing. So if we have 3 languages and you're training 3 different models, that's thrice the energy consumption that you almost thrice, assuming that it takes almost same time. Whether you train the multilingual or monolingual model, there's not much of a difference in the training time of the 2 models. There is a slight difference. So, but I'd say it's still almost 1/3 of that if there are 3 languages involved. And so it's kind of directly proportional to the number of languages that are included in the training. In terms of performance, it probably has yielded marginal improvements in some cases. Generally, in instances like this, we actually have, we expect that at least one of the languages need to have a relatively larger data set. And so there will be a transfer of knowledge and stuff like that. But in this case, we didn't have that. So if that is there, probably we could also see some the performance of the multilingual training going better. Right, so that's it. That's our presentation. Thank you very much. And if you have any questions, I'll be happy to answer.
Any question? Yeah, thanks, Ritesh. Very, now I pass my chair to Surabanga. Surabanga, please.
I think Prasenjit sir is already here, sir. So we have finished.
Yeah, thank you. So we reached at the end of the FIRE 2020. All the presentations are done. Shurupendu, right?
Yes, sir. Yeah.
Great. So I would like to give a big thank you to all of you that during this time of global pandemic, even you help us to arrange this meeting virtually. Hope next year things will be different. We can again see each other in person. And in the steering committee meeting, few decisions were taken. One of them is, I would like to mention it officially now, that from this year, we would like to keep all the shared data in a GitHub account. Soon you will receive some communication from us so that anyone who would like to do an experiment in this area, in your area, in the task that you have offered down the line, so 3 years, 4 years, they need not to search it here and there. There will be a central place where they can actually access with ease. So thank you again. See you in FIRE 2021.